String theory. What if everything you've ever touched, seen, or even thought about isn't made of particles at all, but tiny vibrating strands, far smaller than anything we can directly observe? String theory steps into physics with a bold claim. The universe at its deepest level isn't built from point-like dots, but from microscopic strings, each one oscillating in its own unique rhythm. Change the vibration, and you change the particle. One node becomes an electron. Another becomes a quark. Reality, in this view, is less like a bag of marbles and more like a cosmic symphony. At the heart of this idea is a simple but radical shift. For decades, physicists relied on two towering frameworks: quantum mechanics for the very small, and general relativity for the very massive. Both work stunningly well, until they collide inside extreme environments like black holes or the first split second after the Big Bang. The math falls apart. String theory tries to stitch that tear. By replacing zero-dimensional particles with one-dimensional strings, certain infinities that once wrecked the equations begin to smooth out. Gravity, which stubbornly resists fitting into quantum theory, naturally appears in the mathematics as a vibrating mode of a closed string, what physicists interpret as the graviton. That's a big deal. It suggests a path toward a single framework that unifies all fundamental forces. But the theory doesn't stop there. It demands extra dimensions, far beyond the three of space and one of time we experience. Depending on the version, there may be 10 or even 11 dimensions, curled up so tightly that we can't detect them. These hidden dimensions aren't decorative. They determine how strings vibrate and, therefore, what kinds of particles exist. In some formulations, entire parallel universes emerge from the equations, forming a vast landscape of possible realities with different physical constants. Supporters argue that this mathematical elegance is evidence of something profound. String theory connects ideas from geometry, quantum field theory, and even black hole thermodynamics in ways that have sparked new insights across theoretical physics. It has inspired breakthroughs in understanding entropy and holography, and it has built unexpected bridges between gravity and quantum information. Even if the full theory isn't complete, its tools have proven powerful. Yet the controversy is impossible to ignore. After decades of development, string theory still lacks direct experimental confirmation. The energy scales required to test it are far beyond what current particle accelerators can reach. Critics argue that without testable predictions, it drifts dangerously close to philosophy. Some physicists advocate alternatives like loop quantum gravity, which attempts to quantize spacetime itself without relying on extra dimensions or an enormous landscape of possible universes. Others question whether the theory's flexibility, its ability to accommodate many different outcomes, weakens its predictive power. So where does that leave us? String theory sits in a strange position, mathematically rich, conceptually ambitious, experimentally elusive. It may turn out to be the long-sought theory of everything, or it may be a beautiful detour on the road to a deeper truth. Either way, it has reshaped how physicists imagine the fabric of reality. And perhaps that alone is a sign that, vibrating somewhere beneath our current understanding, something extraordinary is waiting to be heard. Multiverse theory. Imagine a universe not as a lone island in the cosmic ocean, but as a single bubble in an infinite froth of realities. Each bubble, a universe, obeys its own rules, spins its own story, and perhaps contains versions of you living choices you never made. This isn't science fiction. This is the multiverse theory, a radical idea that challenges everything we thought we knew about existence. At the heart of this theory lies the notion that what we call reality may be just one slice of an unimaginably vast ensemble. In one version, you might have taken a different path in life. In another, the laws of physics bend in ways that seem impossible here. The multiverse comes in flavors. The quantum multiverse, where every quantum decision spawns a branching reality. The cosmic multiverse, born from the chaotic inflation of the Big Bang, scattering universes like seeds across a boundless garden. And even the more speculative brain worlds, where entire universes float like sheets in higher dimensions, occasionally brushing and influencing each other. Each idea stretches our imagination and forces us to confront the sheer scale of possibility. Evidence? Well, that's where it gets wild and controversial. Cosmic microwave background anomalies suggest our universe might have bumped into another long ago. Quantum mechanics, with its uncanny superpositions, hints that particles might be whispering secrets of alternate realities. String theory provides a mathematical playground where hundreds, maybe thousands, of universes naturally emerge from the equations. And let's not forget the philosophical allure, the fine-tuning of our universe, the improbable precision of constants that allow life. Feels less like luck and more like one lottery ticket in a stack taller than comprehension. Could the multiverse be the explanation? A cosmic shrug that says, "Of course you exist. There are countless versions of everything." But of course, skepticism waits in the wings. Critics argue that the multiverse is inherently untestable, a seductive story without the backbone of experiment. Some physicists call it more metaphysics than physics, a speculative theater where math dazzles, but reality may never appear on stage. Alternative perspectives insist that we focus on the universe we can observe, urging caution against building castles in the cosmic sand. Even the proponents admit the challenge. Proving the multiverse is like trying to measure an ocean with a teaspoon. You may grasp hints, but certainty slips through. Still, whether real or imagined, the multiverse forces us to think differently. It challenges the arrogance of assuming our universe is the only game in town. It makes every choice, every particle, every heartbeat feel simultaneously monumental and mundane. Are we alone, or are there infinite echoes of ourselves, screaming silently across other realities? The beauty of the multiverse is its ability to unsettle, to inspire wonder, and to remind us that the cosmos might be far stranger than our brains are wired to accept. Whether we ever find proof or simply dance in the shadow of the idea, the multiverse invites us to explore, to imagine, and to marvel at the infinite possibilities that might surround the fragile bubble we call home. Simulation hypothesis. The simulation hypothesis is a fascinating idea suggesting that our universe might be a highly advanced simulation. In other words, everything we perceive, planets, stars, even ourselves, could be part of a constructed reality created by a civilization far beyond our technological level. While this may sound like science fiction, philosophers and scientists have explored it seriously for decades. The concept was popularized by philosopher Nick Bostrom, who proposed that one of three possibilities must be true. Either civilizations never reached the ability to create realistic simulations. Civilizations with such ability choose not to simulate their ancestors, or we are very likely living inside one of these simulations. This means that if advanced civilizations can and do run simulations, it is statistically possible that we are within one. Supporters point to technological trends as potential evidence. Our own progress in computing and virtual reality shows that humans can already create interactive digital worlds. It is conceivable that a far more advanced civilization could create a simulation indistinguishable from what we consider reality. Some also note features of our universe, like the precise mathematical laws and apparent limits in space and time, as patterns that could resemble the rules of a computational system. While these observations are intriguing, they are not definitive proof. Critics, however, highlight important limitations. The hypothesis is difficult, if not impossible, to test directly. There are also questions about why a civilization would run such simulations, and what the purpose might be. Other scientific theories, like the multiverse or undiscovered physical principles, could explain the same observations without invoking a simulated universe. Philosophers note that even if we are in a simulation, our experiences, choices, and relationships still carry meaning and consequence. Ultimately, the simulation hypothesis encourages thoughtful reflection about existence and technology. It reminds us that our understanding of reality is constantly evolving, and it encourages curiosity about the nature of consciousness, the universe, and our place within it. Whether we live in a simulation or not, the idea inspires discussion, exploration, and careful observation of the world around us. Holographic Principle. Imagine everything you've ever touched, seen, or felt, your hands, your memories, the stars, is not truly here in the way you think. The holographic principle proposes something unsettling. The entire universe might be a projection from a distant boundary, like a cosmic hologram. Not a metaphor. Not poetry. Physics. The idea was born from a crisis in black hole physics. When physicists like Stephen Hawking realized black holes slowly evaporate, a paradox exploded into view. If a black hole swallows information, the details of everything that falls in, and then disappears, where does that information go? According to quantum mechanics, information can't simply vanish. Gerard T. Hooft and Leonard Susskind took this problem and flipped reality on its head. What if all the information about what falls into a black hole isn't stored inside it, but on its surface, like data encoded on a two-dimensional boundary? That was the spark. Then came the bold leap. Maybe this isn't just about black holes. Maybe the entire universe works this way. Maybe all the three-dimensional depth we experience is encoded on a faraway two-dimensional surface, the edge of the cosmos. In this view, space itself is emergent. Depth is not fundamental. It's a reconstruction, like a 3D image projected from a flat screen. The mathematics didn't laugh at this idea. In the late 1990s, Juan Meldacena proposed a powerful model known as AD/CFT correspondence. It showed that a gravity-filled universe in higher dimensions could be perfectly equivalent to a quantum theory without gravity in fewer dimensions. Two radically different descriptions. Same physics. It was as if the universe had two languages, one spoken in volume, the other written on a surface. This isn't fringe speculation. The equations line up with black hole thermodynamics, especially the strange discovery that a black hole's entropy, its information content, scales with its surface area, not its volume. That detail is not small. It hints that reality might be fundamentally pixelated on boundaries, not packed into space like we intuitively assume. But let's slow down. Evidence here is mathematical, not experimental. No telescope has captured the edge of the universe storing cosmic code. Some researchers argue the principle works beautifully in certain idealized universes, like Antidas Sitter space, but our universe doesn't neatly fit that model. Others suggest it might be a powerful tool, not a literal description of existence. A computational shortcut, not a cosmic confession. There's also a deeper discomfort. If our universe is holographic, what does that mean for what's real? Are we shadows of data? That question quickly slides from physics into philosophy, and that's where controversy brews. Some critics warn against overstretching the metaphor. Just because two mathematical descriptions are equivalent doesn't mean one is more real than the other. Still, the holographic principle refuses to fade. It stitches together gravity, quantum mechanics, and information theory in a way few ideas can. Whether it ultimately describes the universe or simply reveals a powerful symmetry, it forces us to confront a radical possibility. Depth may be an illusion, and reality may be written on a distant, cosmic screen. If that's true, then everything you call solid might be the universe's version of light on glass, astonishingly detailed, internally consistent, and yet, at its deepest level, a projection. Modified Newtonian dynamics. Imagine you're looking at galaxies far, far away, and you see something strange. The outer stars are moving faster than we thought they should. This mystery has puzzled scientists for decades. Enter modified Newtonian dynamics, or MOND, a theory that flips traditional physics on its head to explain the cosmos without the need for dark matter. MOND argues that Newton's laws of gravity are incomplete and need tweaking, especially in low-acceleration environments, like in the outskirts of galaxies. It's a bold proposition that's earned its fair share of attention. At its core, MOND challenges the conventional understanding of gravity. Newton's laws say that the force of gravity between two objects depends on their masses and the distance between them, and this works perfectly for most situations. But when it comes to the stars on the edges of galaxies, there's a problem. According to MOND, gravity behaves differently when objects are moving slowly enough, in regions where traditional physics can't account for observed speeds. Instead of needing dark matter to explain the high velocities, MOND suggests that gravity simply needs to be adjusted in these low acceleration zones. The evidence for MOND comes from how it fits observed galactic rotation curves. When astronomers measure how fast stars orbit at the edges of galaxies, the speeds are much faster than predicted. Dark matter was initially suggested as the solution to explain this discrepancy. But MOND offers a different take. By tweaking gravity at low accelerations, the observed speeds make sense without invoking invisible mass. MOND has been able to successfully predict the behavior of galaxies in ways that align with observation. No dark matter required. Some scientists claim that MOND explains a broad range of galactic behavior more elegantly than dark matter theories, suggesting that the idea of hidden, undetected mass might not be necessary. However, not everyone is on board. MOND is controversial because it doesn't hold up as well in every scenario. While it works wonderfully at the scale of galaxies, it struggles when applied to galaxy clusters or large-scale cosmic phenomena like the cosmic microwave background. Critics argue that these inconsistencies suggest MOND might not be the complete answer to the mysteries of the universe. Others claim that MOND is merely a patch on an incomplete theory, offering no explanation for phenomena like gravitational lensing, where light bends around massive objects in ways that would still require dark matter. And of course, there's the issue of mainstream acceptance. MOND hasn't been able to match the broad success of dark matter in explaining all aspects of the universe. While it works in certain cases, there's no clear mechanism behind the modifications to gravity proposed by MOND. No underlying principle that could explain why gravity behaves differently in low acceleration regimes. Until that's figured out, many physicists remain skeptical. Still, the ongoing debate between MOND and dark matter is far from over. MOND offers an intriguing alternative to dark matter, challenging the status quo and inviting further investigation into the fundamental forces that govern our universe. Whether it's the key to understanding the cosmos or a dead end, it's clear that MOND has forced us to think differently about gravity, galaxies, and the very nature of the universe itself. Steady-state theory. The steady-state theory, proposed by Fred Hoyle in 1948, challenges the widely accepted Big Bang model of the universe's origin. While the Big Bang suggests the universe began with a singular explosion from a singularity, the steady-state theory presents a radically different idea. According to this view, the universe has no beginning or end, but has always existed in a constant state. As the universe expands, new matter is continuously created to keep the overall density the same. This theory hinges on the belief that the universe is eternal and unchanging on the largest scales, a vision that offers an intriguing yet contentious alternative to the Big Bang. The core of the steady-state theory is that the universe is in a constant, steady state because it is perpetually renewing itself. As galaxies move farther apart, new particles are created in the vast emptiness of space. This not only allows the universe to maintain its density despite expansion, but it also posits that the universe's general appearance remains the same over time. From this perspective, there's no dramatic origin or end, just an eternal, infinite cosmos that is always in a state of dynamic equilibrium. It stands in stark contrast to the Big Bang Theory, where the universe had a definitive beginning, something that many of Hoyle's contemporaries found both fascinating and controversial. When we dive into the evidence, it's easy to see why this theory caught the imagination of some scientists. The primary support for the steady-state theory came from its elegant explanation of cosmic expansion. The idea that the universe was always the same, despite its growth, offered a clear picture of an unchanging cosmos. However, as astronomy advanced, new evidence began to challenge this view. The discovery of cosmic microwave background radiation, CMB, in 1965 dealt a massive blow to the steady-state model. This radiation, a leftover afterglow from the Big Bang, provided substantial proof of a universe with a singular beginning. The CMB directly contradicted the notion of a steady, eternal universe, as it represented a physical remnant of the universe's early hot and dense state. With this, most astronomers shifted their allegiance to the Big Bang Theory. However, there's still a segment of scientists who view the steady-state theory as a valuable contribution to the field. While largely discredited in its original form, some ideas within the theory, like the continuous creation of matter, have found their place in more modern cosmological models. For example, the theory of quantum fluctuation and some forms of multiverse hypotheses have sparked interest. Moreover, certain cosmologists still argue that there are aspects of the universe that might support the concept of an eternally existing cosmos, even if the full steady-state model doesn't hold. In closing, while the steady-state theory may no longer hold the mainstream scientific community's favor, its challenges to the conventional wisdom pushed the boundaries of cosmological thought. It reminded scientists to question, to imagine, and to reconsider our understanding of the universe's origins. Today, even as the Big Bang Theory remains dominant, there are still questions that linger, many of which echo the same curiosity that once propelled the steady-state theory forward. It's a reminder that our view of the cosmos is still evolving. Electric Universe Hypothesis. The universe we were taught about runs on gravity. Stars form because clouds collapse. Galaxies spin because of invisible dark matter. Black holes dominate the centers of cosmic cities. That's the standard story. But the electric universe hypothesis steps in and says, what if gravity isn't the main actor? What if electricity, the same force that sparks lightning and powers your phone, is shaping the cosmos on a massive scale? At its heart, this idea argues that space isn't empty and electrically neutral the way mainstream astrophysics often assumes. It claims plasma, ionized gas that carries electric currents, fills the universe and forms enormous cosmic circuits. Supporters point to plasma physics experiments showing filament patterns that look strikingly similar to the web-like structure of galaxies. They argue that Birkeland currents, twisting filaments of charged particles observed in Earth's magnetosphere, scale up to galactic proportions. Instead of gravity alone sculpting spiral galaxies, they suggest electromagnetic forces pinch and shape them. In this view, stars may not ignite purely from gravitational collapse, but from electrical interactions within plasma. Even some planetary scars, like massive craters and canyons, are interpreted by proponents as evidence of past electrical discharges between celestial bodies. Advocates often bring up how powerful electromagnetic forces are compared to gravity. On small scales, electricity easily overpowers gravity. So the question they raise is simple. If plasma dominates visible matter in the universe, why wouldn't electric forces matter on cosmic scales too? They also highlight unresolved puzzles in conventional cosmology, like the need for dark matter and dark energy, entities we infer but haven't directly detected. To them, these are signs that something fundamental might be missing. Plasma cosmology pioneers such as Hannes Alfvén, a Nobel Prize-winning physicist, argued that ignoring plasma behavior in space was a serious oversight. Electric universe supporters see themselves continuing that line of thinking. But here's where the friction builds. The overwhelming majority of astrophysicists reject the electric universe model. They argue that while plasma effects are real and important in certain environments, like the Sun or nebulae, large-scale cosmic observations consistently support gravity as the dominant force. Precise measurements of the cosmic microwave background, gravitational lensing, and galaxy cluster dynamics align strongly with the standard cosmological model. Critics also point out that electric universe claims often lack detailed mathematical frameworks capable of making testable predictions. In science, looking visually similar isn't enough. You need equations that work under scrutiny. So far, mainstream researchers argue, gravity-based models simply outperform electrical alternatives when it comes to predictive accuracy. There's also the issue of scale. While electromagnetic forces are stronger than gravity, large bodies tend to be electrically neutral overall, meaning their charges cancel out. Without large net charges, electric forces don't dominate the way proponents suggest. For critics, this isn't a conspiracy or close-mindedness. It's about consistency with data collected from satellites, telescopes, and particle detectors. Still, the electric universe hypothesis continues to attract attention. It challenges authority, questions assumptions, and invites people to rethink cosmic fundamentals. Whether it's a revolutionary insight waiting for validation or a compelling but flawed detour, it serves as a reminder that science thrives on bold questions. The universe is vast, strange, and not fully understood. And sometimes, even controversial ideas keep the conversation charged. Time cube. You've probably never heard anything like time cube. It's not a new video game or a bizarre math trick. It's a theory so out there that it makes you question the very way you think about time. Its creator, Jean Ray, claimed that everything taught in schools about time, physics, and science is not just wrong, but completely upside down. He believed that each day isn't a single linear march from sunrise to sunset, but actually consists of 4 simultaneous days happening at once. Sounds insane? That's exactly the point. At the heart of Time Cube is this radical idea. The standard concept of time is a lie designed to keep people blind to reality. According to Ray, every 24-hour rotation of Earth splits into 4 corners: sunrise, midday, sunset, and midnight. Each of these corners operates as its own separate day, happening simultaneously. So, what we experience as a single day is really a chaotic overlap of 4 distinct realities. He called this cubic time, a concept that turns everything we assume about clocks, calendars, and even human experience on its head. It's the kind of thinking that challenges not just science, but logic itself. Evidence for time cube is tricky. Ray often used a mix of mathematics, personal observation, and extreme interpretations of physics. He pointed to what he saw as inconsistencies in conventional science: the arbitrary way we divide days into 24 hours, the way education enforces a linear worldview, and the supposed arrogance of scientists who dismiss anything outside their rigid framework. He claimed that if you actually looked at the sky, the sun, and the passage of time carefully, you'd see the 4-day reality. His website, lectures, and rambling essays became a shrine to this vision, filled with diagrams, charts, and passionate arguments about how modern thinking is fundamentally stupid for ignoring the cube. But Here's where the controversy skyrockets. Mainstream science absolutely rejects time cube. Physics doesn't support the idea of 4 simultaneous days, and no empirical studies confirm Ray's claims. Critics argue that time cube is less a theory and more a performance art of radical thinking, a fascinating glimpse into a mind completely untethered from convention. Others have tried to interpret it metaphorically, seeing it as a critique of rigid education systems rather than a literal scientific claim. And yet, the theory persists online as a curious meme of intellectual rebellion. People either dismiss it as lunacy, or they admire the sheer audacity of challenging centuries of accepted knowledge with nothing but raw conviction. In the end, time cube exists in a strange zone between philosophy, satire, and genuine belief. It asks you to consider how much of what we accept about reality is imposed. How rigid is our understanding of time and space? Even if you don't buy into the literal concept, the idea forces a mental reckoning about the way knowledge is structured and the power of challenging the official narrative. Love it or hate it, time cube doesn't just fade quietly. It lingers, a four-cornered echo in the minds of those brave enough to glimpse its chaos. Variable speed of light. Imagine a universe where the speed of light isn't a cosmic speed limit, but more like a suggestion. That's the wild ride the variable speed of light, or VSL, theory takes us on. It flips one of Einstein's cornerstones on its head, suggesting that light might have traveled faster, or slower, at different times in the universe's history. This isn't just sci-fi fodder. It's an attempt to solve some of cosmology's trickiest puzzles without invoking mysterious forces like dark energy or inflation. At its heart, VSL challenges the idea that the speed of light is fixed. Traditionally, the speed of light is the ultimate cosmic constant, dictating causality and the structure of space-time. But what if, in the first split seconds after the Big Bang, light raced through space at an insanely higher speed? That would explain why distant regions of the universe look surprisingly similar despite supposedly never having had enough time to interact. It's a bold tweak to the laws of physics, suggesting that constants may not be as constant as we thought. Evidence for this idea comes from both theoretical models and attempts to explain observational anomalies. Some physicists point out that VSL could resolve the horizon problem, a puzzle about why the cosmic microwave background is so uniform. Others argue it might offer a smoother alternative to inflation, the standard explanation that invokes a hyper-rapid expansion of the universe. Researchers have even developed mathematical frameworks where the speed of light evolves dynamically, tweaking equations in ways that surprisingly match certain cosmological observations. While we haven't measured a fluctuating speed of light directly, these models give us new lenses to interpret early universe phenomena that standard models struggle to explain. Of course, VSL isn't without its critics. Many argue that tampering with the speed of light is too radical, threatening the very foundations of relativity. Einstein's equations are notoriously picky. Mess with a core constant, and you risk tearing apart everything built on it. There's also the question of experimental evidence. So far, there's no smoking gun proving that light ever ran faster or slower. Alternative interpretations, like inflationary models or variations in other fundamental constants, offer explanations without rewriting the cosmic rulebook. And some philosophers and physicists worry that VSL could open the door to untestable speculation, flirting dangerously with ideas that sound amazing but may never be provable. Still, the appeal of VSL is hard to ignore. It pushes us to ask uncomfortable questions. What if our laws of physics aren't universal, but time-dependent? Could constants be local, fluctuating features rather than rigid fixtures? Even if VSL never becomes mainstream, it forces cosmologists to rethink assumptions, to test the universe in ways they hadn't imagined. In the end, it's a reminder that science isn't static, It's a conversation with reality, constantly questioning what we think we know. DSL might be controversial, but it's a conversation starter, a spark that keeps our cosmic curiosity alive, daring us to imagine a universe far stranger and more flexible than we've ever accepted. Boltzmann Brain. Imagine waking up one day and realizing, shockingly, that the entire universe around you might just be a fleeting hallucination of your own mind. Sounds like a sci-fi plot, right? But some of the sharpest minds in physics aren't joking. Enter the concept of the Boltzmann brain, a bizarre idea that forces us to question reality itself. It's named after Ludwig Boltzmann, a 19th century physicist obsessed with the chaotic dance of particles and entropy. The twist? He didn't imagine this scenario explicitly, but modern cosmologists have taken his thoughts on statistical fluctuations and run wild with them. A Boltzmann brain is essentially a fully formed conscious mind, complete with memories, popping into existence purely by chance in a chaotic universe. No body, no planet, no universe around it, just a brain that believes it exists in a coherent reality. At its heart, the Boltzmann brain theory is a confrontation with probability. In a universe that is infinite, or just vast enough, extremely unlikely events eventually happen. Entropy, the measure of disorder, isn't just a background concept, it's the engine. Over immense stretches of time, it's argued, random particles could spontaneously organize themselves into a functional brain, complete with fleeting but convincing perceptions of a universe. That means that statistically, it might be far more likely for a solitary brain to appear than for the entire structured universe we observe to exist exactly as it does. In other words, from a cold math perspective, you might actually be a Boltzmann brain, momentarily experiencing this coherent dream of reality. Evidence for this is more philosophical than empirical. The arguments lean heavily on cosmology, thermodynamics, and probability. Infinite universe models, combined with entropy-driven fluctuations, make the existence of such spontaneous brains almost inevitable if the universe lasts long enough. Some physicists argue that the apparent fine-tuning of our universe, or even our perception of time moving forward, is consistent with the rare but inevitable occurrence of these random consciousnesses. It's not that there's a laboratory experiment proving you're a hallucinated brain. It's that the math of infinite possibilities doesn't rule it out. But here's where it gets messy. The Boltzmann brain idea sparks discomfort precisely because it undermines our trust in observation. If brains that appear randomly vastly outnumber normal observers, how do we know we're not one of them? Critics argue this leads to a paradox. Any theory predicting a universe dominated by Boltzmann brains might be fundamentally flawed because our coherent observations would be improbable under that model. Alternatives suggest tweaks to cosmology or constraints on entropy to ensure that ordinary observers like us remain far more probable than isolated, spontaneous brains. In essence, many physicists treat Boltzmann brains as a theoretical headache rather than a likely reality, an alarm bell signaling something missing in our understanding of the universe. So what do we make of it? The Boltzmann brain is less a literal prediction and more a philosophical shockwave. It asks us to confront probability, reality, and the strange loneliness of existence in a vast, indifferent cosmos. Are we reliable witnesses to the universe, or just fleeting sparks of order in an endless sea of chaos? Even if we never find definitive proof, the idea forces a humbling perspective. Reality might be far more fragile and mysterious than we dare imagine. Panspermia. Imagine the universe as a giant cosmic soup, with life not necessarily starting here on Earth, but hitching a ride across the stars. That's the wild idea behind panspermia. It flips the whole origin of life story on its head. Maybe life didn't evolve from a primordial stew in a puddle on Earth, but instead arrived as microscopic stowaways aboard asteroids, comets, or interstellar dust. Suddenly, Earth is just one stop on an intergalactic road trip for life. The core of this concept rests on a simple, almost poetic principle. Life is incredibly tough. Bacteria and spores can endure extremes that would annihilate complex organisms. Radiation, vacuum, freezing temperatures, even decades of drifting through space. Some microbes can survive it all. If life can cling to rocks ejected from one planet, it could theoretically travel vast cosmic distances. Then, when these space travelers crash into another planet, like Earth, they might seed life all over again. Evidence supporting this idea isn't purely science fiction. Meteorites found on Earth sometimes carry organic molecules, complex carbon compounds that are life's building blocks. Take the famous Murchison meteorite, which crashed in Australia in 1969. It contained amino acids not just native to Earth. Experiments in orbit have shown bacterial spores surviving for years under harsh cosmic conditions. And planets and moons within our own solar system, Mars, Europa, Enceladus, have environments where life might exist or have existed, potentially sending material outward. It's tantalizing, the thought that Earth's life might be a cosmic import. Of course, skeptics raise their eyebrows. Surviving the ejection from a planet without being destroyed by shock, traveling light years, and crashing safely, these are high hurdles. Critics argue it's a convenient excuse for gaps in our understanding of life's origins rather than a proven fact. Others suggest alternatives, like life emerging independently on multiple worlds, because chemistry naturally tends toward complexity under the right conditions. There's also the notion of directed panspermia, the idea that life might have been intentionally spread by some advanced civilization. Controversial? Absolutely. Plausible? Maybe more than we'd like to admit. Whether you're convinced or not, panspermia forces us to think bigger. Life might not be a unique miracle confined to a single planet. Instead, it could be a universal passenger, hopping from one world to another, adapting and persisting wherever conditions allow. The controversy lies not just in the evidence, but in what it implies. If life came from somewhere else, then every discovery of life elsewhere isn't just an alien organism. It's potentially our distant relative. It challenges Earth-centric thinking and invites a humbling, almost philosophical perspective. We might be less the originators of life and more caretakers of a cosmic legacy that stretches across galaxies. Lamarckism. Imagine a world where creatures could shape their own future simply by trying hard enough. That was the radical idea Jean-Baptiste Lamarck threw on the table back in the early 1800s. Forget Darwin's slow grind of natural selection. Lamarck suggested that if an organism used a body part more, it could strengthen it, and then, here's the kicker, it could pass that upgrade directly to its offspring. Think of a giraffe stretching its neck to reach higher leaves and suddenly giving birth to a baby with a longer neck. Pretty wild, right? At the heart of Lamarckism are a few core ideas. First, use and disuse. Organs or features that get exercised grow stronger, while those ignored shrink or disappear. Second, the inheritance of acquired characteristics. Whatever changes an organism gathers over its lifetime can be handed down to the next generation. Third, a sort of internal drive. Lamarck thought life had a natural push toward complexity and perfection, so evolution wasn't random chaos, but a purposeful journey toward better forms. Supporters of Lamarckism point to some quirky examples that seem to fit. Blacksmiths with big muscular arms theoretically producing stronger-armed kids. Domesticated animals showing traits that humans selected for within a generation. Even some early experiments with worms and plants seem to hint that environment could directly tweak future generations. Lamarck's ideas were appealing because they gave a sense of control. Organisms weren't just at the mercy of nature, they were co-authors of their own evolution. But critics have a lot to say. Modern genetics shows that the DNA in our eggs and sperm doesn't just rewrite itself because you exercised your arms or learned piano. Traits acquired during life usually don't sneak into the next generation's genome. Darwin's natural selection explains adaptation without invoking magic inheritance. Variations appear randomly, and the environment decides which stick around. Some might argue Lamarck underestimated the power of chance and overestimated the ability of life to self-improve on command. Yet, Lamarckism isn't entirely dead. Epigenetics has given it a new lease on life in a strange twist. Certain environmental effects, like famine or stress, can leave chemical marks on DNA that influence gene expression in offspring, at least temporarily. So, in a weird sense, Lamarck wasn't totally off base. Life does sometimes carry the echoes of experiences forward, even if not in the exact way he imagined. So where does that leave us? Lamarckism is a fascinating mix of myth and insight, a bold vision of evolution as a proactive, almost heroic process. While classic genetics has largely sidelined it, the story of acquired traits still whispers in the margins of modern science. It's a reminder that evolution might be more inventive, quirky, and complex than we give it credit for, and that even ideas once dismissed as wrong can inspire fresh ways of thinking about life's endless dance with change. Gaia Hypothesis. Imagine Earth as a single living, breathing entity. That's basically what the Gaia Hypothesis suggests, that life and the planet are not separate, but intertwined in a cosmic dance, constantly regulating the environment to sustain life. It's a bold way of thinking about Earth, flipping the usual nature as a backdrop mindset on its head. James Lovelock, the mind behind it, proposed that every organism, from plankton in the ocean to massive forests, plays a role in keeping conditions just right: temperature, atmosphere, chemistry, like a planetary thermostat tuned over billions of years. At its heart, Gaia isn't claiming the Earth is conscious or intentional. It's more like a self-regulating system. Microbes release chemicals that affect the air and oceans. Plants influence rainfall and climate. Even animals can alter their environment, nudging it in ways that maintain the balance of life. It's a web where every thread, big or small, matters. The idea is radical because it frames evolution and ecology as collaborative, not just competitive. Life doesn't just adapt to Earth. Together, life and Earth adapt to maintain stability. Evidence for this is scattered but intriguing. Think about the oxygen in the atmosphere. It didn't just appear by accident. Cyanobacteria pumped it out billions of years ago, changing the planet's chemistry and making it habitable for complex life. Ocean plankton regulate cloud formation by releasing compounds that seed clouds, literally affecting climate. Coral reefs shape coastlines, protecting biodiversity and maintaining ecosystems. Even seemingly destructive events, like forest fires, can cycle nutrients and trigger regrowth, contributing to long-term equilibrium. Some climate models even use Gaia-like feedback loops to explain why Earth's environment has remained relatively stable despite astronomical and geological upheavals. But not everyone buys the hype. Critics argue Gaia risks sounding mystical, suggesting Earth is deliberately keeping itself alive. Skeptics point out that feedback loops can stabilize or destabilize, and chaos can reign just as easily as balance. Alternative views, like Earth system science, focus on feedbacks without implying purpose. Evolutionary biologists question whether natural selection alone could produce the kinds of planetary self-regulation Gaia implies. In short, the hypothesis is more metaphor than strict scientific law, though a metaphor that makes you reconsider the scale and interconnection of life. Whether you see Gaia as a poetic vision or a controversial theory, it forces us to rethink humanity's place. If life and Earth are codependent, then messing with one inevitably disrupts the other. Climate change, deforestation, ocean acidification. These aren't just local problems. They ripple through the planet-wide system. The Gaia Hypothesis challenges the idea that humans are outside nature, showing instead that we're participants in an intricate, ongoing negotiation with the planet. Love it or doubt it, Gaia makes one thing clear: Earth isn't passive. It's alive in a way we're only beginning to understand, and every choice we make matters. Aquatic Ape Hypothesis. Imagine a time millions of years ago when our ancestors were wandering the African landscapes, but some weren't sticking strictly to the savanna. What if a group of early humans started spending more time in water? That's the heart of the Aquatic Ape Hypothesis, a theory that suggests some human traits evolved because our ancestors were wading, swimming, and foraging in rivers, lakes, or coastal areas. It's bold, a bit splashy, and definitely controversial, because it challenges the traditional view that humans evolved mostly on dry land. So what's the deal? The hypothesis proposes that some of the quirky things that make humans different from other primates, like our relative hairlessness, fat distribution under the skin, ability to hold our breath, and upright posture, might make more sense if you picture early humans as semi-aquatic. Think about it. Hairlessness could reduce drag in water, fat layers might help with buoyancy and insulation, and walking upright frees your hands to carry food from a riverbank. Even our noses and ears, which can close underwater, could fit into this watery lifestyle picture. In short, the theory says, baby humans adapted to water, not just to savanna heat. Evidence supporting this idea is quirky but intriguing. Marine mammals, like seals and dolphins, show similar adaptations for water life, and humans share some traits that seem unusual for land mammals. Babies instinctively swim when placed in water, and some human physiological quirks, like the diving reflex, echo patterns found in aquatic creatures. There's also the fact that certain foods, like shellfish and fish, could have been rich sources of nutrients that fueled brain growth. Advocates argue that these pieces together make the hypothesis more than just a splashy thought experiment. They suggest a lifestyle that could have left evolutionary fingerprints. But, as compelling as it sounds, this hypothesis isn't mainstream. Critics point out that many traits the aquatic theory highlights can be explained by other environmental pressures. For example, hairlessness might be linked to cooling efficiency on the hot savanna, and fat distribution could relate to energy storage rather than insulation in water. The fossil record is sparse on direct aquatic evidence, like footprints or tools tied to water foraging, and comparing humans to fully aquatic animals can sometimes feel like stretching the analogy too far. Other theories, like thermoregulation or bipedalism for open land efficiency, offer simpler explanations without dragging us into water. Still, the aquatic ape hypothesis sparks the imagination. Even if it isn't the dominant theory, it pushes scientists to think outside the box about human evolution. Maybe we weren't just creatures of grass and trees. Maybe some of us were also explorers of shallow rivers, wading and gathering food, testing the limits of both land and water. It's a reminder that evolution isn't a straight path, and our story could be more surprising than textbooks suggest. Whether it's a real explanation or a provocative thought experiment, it forces a splash of curiosity into how we think about ourselves. Evolution, after all, might be stranger and wetter than we like to admit. Young Earth Creationism. You know, when people hear about the age of the Earth, most automatically think billions of years, ancient fossils, and distant galaxies. But then, there's this whole other crowd, young Earth creationists, who argue, quite boldly, that the Earth is way younger, just around 6,000 to 10,000 years old. It's not just a number for them. It's tied to a worldview that reads the Bible as a literal historical account. And that perspective colors how they see everything, from the Grand Canyon to distant stars. At the heart of young Earth creationism is the idea that God created the world in 6 literal days, not long periods or metaphorical epochs, 6 normal-length days. They hold that Adam and Eve were real people, the global flood described in Genesis actually happened, and dinosaurs coexisted with humans. It's a complete alternate timeline of history, one that flips conventional science on its head. For adherents, science isn't a tool to challenge Scripture. It's something to interpret in a way that fits Scripture. So when they see fossils, ice cores, or geological layers, they don't read them as millions of years of slow change. They see evidence of rapid, catastrophic events. Their arguments are surprisingly detailed. For instance, they point to the decay of Earth's magnetic field and argue that a young Earth fits better with measured data than billions of years. They claim that soft tissue in dinosaur fossils defies expectations because it shouldn't survive millions of years. And then there's the flood narrative, citing massive sediment layers, coal seams, and even the fossil record as leftovers from a global deluge. It's a perspective that makes nature seem like a puzzle designed to point back to Scripture, with every rock layer, fossil, or star having a purpose in the story. But of course, critics are loud. Geologists, astronomers, and biologists point out that the evidence for an ancient Earth is overwhelming. Radiometric dating, the speed of light from distant stars, and ice cores spanning hundreds of thousands of years all scream old Earth. The fossil record shows a progression of life, not a sudden, fully formed world. Even the idea that a global flood could deposit all sediment layers, while leaving no trace of worldwide chaos, is highly questionable. Alternative religious interpretations suggest that the Genesis account could be metaphorical, poetic, or symbolic, allowing for billions of years of cosmic history without undermining faith. Yet, here's the kicker. Young Earth creationism persists, not just because of evidence or theology, but because it answers a human need for certainty. It's a world where everything has a clear cause, a divine purpose, and a timeline you can understand. In a way, it's a counterculture to mainstream science, a reminder that humans love stories that make sense of complexity. Whether you side with the literal interpretation or lean towards scientific consensus, young Earth creationism forces a conversation about faith, knowledge, and how we decide what counts as truth. It's not just about rocks and fossils. It's about the stories we tell ourselves to make sense of where we come from and why we're here. And maybe that's why, despite the controversy, it continues to spark debate centuries after it first emerged. Intelligent design. Imagine staring at a watch and wondering how it came together without a watchmaker. That's the kind of question intelligent design throws at us, but in a biological sense. The idea suggests that life's complexity isn't just the result of random chance and natural selection. It's the product of some guiding intelligence. Not necessarily religious, not necessarily supernatural, but something with enough know-how to set the blueprint in motion. It challenges the mainstream narrative that evolution alone is the ultimate explanation for life. At its heart, intelligent design hinges on complexity. Think about the human eye or a bacterial flagellum. These structures aren't just complicated, they're interdependent. Pull out one part, and the whole system stops working. Proponents call this irreducible complexity, arguing that natural selection couldn't gradually assemble such features because partial versions wouldn't function. There's also the notion of specified complexity, where patterns in DNA and molecular machinery appear so precise that chance alone seems implausible. Essentially, life carries signatures that look suspiciously like they were planned. Evidence often cited is fascinating and sometimes eyebrow-raising. Molecular machines in cells resemble intricate devices engineers would be proud of. The bacterial flagellum, for example, acts like a rotary motor with dozens of parts working in perfect sync. Some proteins and genetic circuits appear, fine-tuned to achieve specific outcomes. Advocates point to the improbability of these arrangements forming purely through mutations and selection, claiming that probabilities are too low for randomness to account for them. Even certain constants in physics, like the gravitational constant or the strength of electromagnetic forces, are sometimes woven into the discussion, suggesting that the universe itself is calibrated for life. Of course, no controversy exists without critics. Evolutionary biologists argue that irreducible complexity is misleading. Systems can evolve from simpler precursors through co-option or gradual modification. The eye, once thought impossible to evolve, is now understood as a sequence of small improvements over millions of years. Critics also warn that intelligent design can masquerade as science while relying on gaps in knowledge as proof, a tactic called the "God of the gaps" argument. Alternative perspectives, like natural selection plus genetic drift, show that complexity can emerge naturally, albeit unpredictably. The debate is as much philosophical as scientific, teetering between what we can measure and what we intuitively sense about purpose and design. Still, the discussion is far from dull. Intelligent design forces us to ask bigger questions. Why does life look designed? Are there patterns in nature that scream intention, or do we just recognize order because humans crave it? Whether you lean toward design or evolution, pondering these questions makes the science of life more thrilling. The controversy isn't just about biology, it's about the very lens through which we view existence. And maybe, just maybe, the wonder of life is amplified whether we see it as carefully planned or as a chaotic masterpiece shaped by chance. Epigenetic inheritance. Imagine a world where your experiences, what you eat, even the stress you endure, could leave marks not just on your own body, but on the bodies of your kids and grandkids. That's the eerie and fascinating reality epigenetic inheritance teases. Unlike classic genetics, where DNA is the unchanging script of life, epigenetics is like post-it notes slapped on that script, sometimes permanent, sometimes fleeting, modifying how genes behave without altering the letters themselves. It's the biological equivalent of leaving breadcrumbs for the next generation. But here's the twist. Some breadcrumbs lead to disease, others to resilience. At the core, epigenetic inheritance revolves around chemical tags, like DNA methylation or histone modification, that tweak gene expression. Think of them as dimmer switches on a lamp. The gene is the bulb, and the tags decide how bright it shines, or if it even turns on. These tags respond to environment, diet, stress, toxins, and even social interactions. What's wild is that some of these switch settings can survive the rigorous reset process during reproduction, effectively carrying environmental stories across generations. It's like your ancestors texting advice or warnings directly to your genes. Evidence keeps trickling in and, honestly, it's both thrilling and unsettling. Studies with mice have shown that a traumatic experience or famine exposure can alter DNA methylation patterns, affecting stress response, metabolism, or behavior in offspring. Human research hints at similar patterns. Children of Holocaust survivors show altered stress hormone profiles, and descendants of people exposed to severe famine decades ago have higher susceptibility to metabolic disorders. The weight of lifestyle choices suddenly feels heavier, because your decisions may ripple further than your own lifetime. Yet, as fascinating as it is, this field courts controversy. Critics argue that separating true inherited epigenetic changes from environmental influence is tricky. Are we really passing on chemical marks, or just recreating similar conditions for the next generation? Reproducibility in humans is another sticking point. Some findings struggle under repeated experiments. And let's not forget the evolutionary debate. Are these changes a sophisticated survival tool, or mostly biological noise that occasionally sticks around? Some researchers push for skepticism, warning against overblown claims that epigenetics can fully explain inheritance of trauma or behavior, urging careful distinction between correlation and causation. Still, dismissing epigenetic inheritance entirely would be like throwing out the possibility of ghosts because we can't see them clearly. There's something undeniably provocative here. Biology may not be as deterministic as once thought. Our genes are scripts, but the annotations we and our ancestors add might guide not just our story, but theirs too. It's messy, it's imperfect, and yes, it challenges the classic notion of heredity, but it opens doors to understanding disease, adaptation, and even societal health from a generational lens. The idea that our bodies carry echoes of ancestral lives is no longer pure speculation. In fact, it forces us to rethink responsibility, environment, and the silent conversations happening inside our DNA. Epigenetic inheritance is more than a scientific curiosity. It's a narrative of connection, consequence, and caution. It tells us our biology is alive, responsive, and maybe even moral, in a way that intertwines generations. The debate will rage, experiments will refine, but one thing is clear: the genes we inherit might just carry more than blueprints, they may carry stories. Directed evolution by viruses. Viruses are nature's ultimate hackers. They sneak into cells, rewrite DNA, and spread their changes with alarming efficiency. But what if we could channel that chaos? Directed evolution, when guided by viruses, isn't just sci-fi fantasy. It's a real scientific strategy, one that's reshaping how we think about genetics. Instead of waiting millions of years for slow, random mutations, scientists can exploit viral machinery to accelerate evolution on demand. Imagine turning a virus into a tiny, microscopic laboratory, forcing proteins to evolve new abilities faster than nature ever could. It's bold, it's risky, and it's changing the rules of the biological game. At the heart of this idea is the virus's uncanny ability to copy and mutate. Certain viruses, like bacteriophages, inject their genetic material into host bacteria and churn out countless offspring, each slightly different from the last. Scientists harness this process by inserting a gene of interest into the viral genome, then letting the virus experiment with variations in real time. Selection comes next. The viruses that produce desirable traits survive and replicate, while the rest are discarded. Repeat this cycle over several rounds, and suddenly, a protein that once worked one way is now optimized for an entirely new function. The elegance lies in simplicity: mutation plus selection, amplified by the virus's natural efficiency. Evidence of success is piling up. In labs across the globe, researchers have used viral-assisted directed evolution to create enzymes that break down plastics, proteins that detect toxins, and even molecular machines with completely novel functions. One striking example involves phage-assisted continuous evolution, PACE, where viruses evolve target proteins in a matter of days rather than decades. Traditional methods would require painstaking manual mutations and screenings. Here, the virus does the heavy lifting, providing a speed and scale that's unprecedented. The argument for this approach is persuasive. If viruses can naturally innovate at dizzying speeds, why not put that power to work for human challenges in medicine, industry, and environmental solutions? Yet the approach is not without controversy. Critics warn that unleashing mutating viruses, even in controlled environments, is flirting with unpredictability. Evolution is inherently chaotic, and while scientists try to cage the process, mutations don't always read the instruction manual. There's also an ethical debate. Are we comfortable accelerating evolution artificially, potentially creating entities no one fully understands? Alternatives exist, like computational protein design or synthetic biology circuits, which provide more predictable outcomes without relying on viral chaos. Still, these methods often lack the sheer adaptive power that viruses naturally bring to the table. leaving a trade-off between control and evolutionary speed. Ultimately, directed evolution by viruses is a bold gamble at the frontier of biology. It challenges our comfort with control, forcing us to trust in a system designed by nature yet co-opted for human ends. The results are provocative, promising faster solutions to some of our toughest scientific problems, but they also demand vigilance, ethical reflection, and rigorous containment. In harnessing viral power, we glimpse a future where evolution is not just observed, it is directed, fast-tracked, and weaponized for progress. And while the risks are real, the potential to transform medicine, industry, and environmental management makes this one of the most fascinating, provocative experiments humanity has ever attempted. Mirror life hypothesis. Imagine a universe where life isn't exactly like ours, not just in culture or shape, but in the very chemistry that forms its building blocks. That's the essence of the mirror life hypothesis. Instead of the familiar left-handed amino acids and right-handed sugars that dominate earthly biology, mirror life would flip that script. Everything we know about biology would run in reverse, like a cosmic reflection. It's not science fiction. It's a provocative thought experiment with deep implications for how we search for life beyond our planet. At its core, the hypothesis challenges the assumption that life must look like us at the molecular level. Our biochemistry isn't just convenient, it's a historical accident, possibly one of countless outcomes among many chemical possibilities. Mirror life isn't necessarily hostile or exotic in behavior. It could breathe, metabolize, and reproduce in ways that seem utterly familiar but be invisible to our standard detection methods. The idea forces scientists to question, are our methods for detecting extraterrestrial life too narrow, too biased toward our own mirror? Evidence supporting the plausibility of mirror life is subtle but intriguing. Laboratory experiments show that left and right-handed molecules can exist, and reactions can proceed in mirrored forms. There's no inherent chemical law forbidding one form over the other. Meteorites, like the famous Murchison, contain both left and right-handed amino acids, hinting that the universe doesn't care which handedness life might adopt. Even on Earth, tiny chemical imbalances suggest natural processes could easily tip the scale in either direction. This isn't proof of mirror life, but it's enough to suggest the concept isn't pure fantasy. It's grounded in real chemical possibility. Critics argue that mirror life is more thought experiment than reality. They point out that if mirror life existed in proximity to Earth-like life, it might be incompatible at a fundamental level. Immune systems, enzymes, even digestion could fail catastrophically in cross-contact scenarios. Others suggest that if mirror life were common, we might have detected anomalies in chemistry around Earth or in distant starlight, yet no such signs appear. Alternatives propose that life could evolve exotic biochemistries without full mirroring, like silicon-based cells or radically different energy metabolisms, which might be more plausible than a perfect chemical mirror. Still, the mirror life hypothesis sparks a unique kind of curiosity. It stretches imagination while demanding a rethink of how we hunt for life in the universe. It's a reminder that our Earth-centric lens might blind us to entirely valid forms of life right under, or above, our observational noses. It invites the possibility that the universe is playing with a palette we barely imagined, and that life's blueprint could be as much about chance and chemistry as it is about inevitability. In the end, mirror life remains hypothetical, perhaps even improbable, but it refuses to be ignored. Whether it exists or not, the hypothesis reshapes the conversation about what life can be, how fragile our assumptions are, and how much of the universe might be reflecting possibilities we've yet to recognize. Sometimes, seeing ourselves in reverse is the only way to truly understand what life could look like beyond the mirror. Genetic memory theory. Imagine if the memories of our ancestors weren't just stories passed down in books or whispered around fires, but something woven into our very DNA. Genetic memory theory dares to suggest just that experiences, fears, skills, even traumas, could be inherited biologically, shaping who we are without a single conscious lesson. It's a provocative idea that blurs the line between nature and nurture, challenging the way we think about identity and personal history. At its core, the theory claims that our genes don't just code for physical traits, like eye color or height, but can carry the echoes of lived experiences. Think of it as biological déjà vu. Instincts, reactions, and patterns in our behavior might be fingerprints left by generations past. Some proponents argue that phobias, for example, could be hardwired survival mechanisms passed down from ancestors who faced real dangers, like an irrational fear of snakes or heights. Others take it further, proposing that skills, from hunting strategies to social instincts, might be encoded in our genome, waiting to be unlocked under the right circumstances. Evidence for genetic memory comes from an intriguing mix of studies. Experiments in animals have shown that mice trained to fear certain smells can produce offspring that react fearfully to the same odors, even if the babies never experience the threat themselves. In humans, researchers point to trauma studies suggesting children of people who endured extreme stress or famine show altered stress responses or metabolic changes. Neuroscientists and epigeneticists talk about chemical tags that can modify gene expression and, crucially, can sometimes be passed on. It's tantalizing because it hints at a bridge between lived experience and inherited biology, a kind of memory outside the mind. But the theory is far from settled, and skepticism runs deep. Critics argue that what looks like genetic memory could simply be learned behavior within family environments or cultural transmission rather than DNA. The mechanisms aren't fully understood, and there's a huge leap from chemical changes in genes to the storage of complex memories. Some scientists warn that overhyping the idea risks slipping into genetic determinism, reducing the messy, personal, and social aspects of human life to mere biology. Others propose alternatives, like collective unconscious theories or purely environmental explanations, which don't rely on inherited molecular memory but still account for recurring patterns across generations. Whether you see it as a revolutionary lens or an overblown hypothesis, genetic memory theory forces us to rethink how much of us is truly ours. Are we shaped only by our own choices and experiences, or are we living echoes of everyone who came before? Even if the concept remains controversial, it nudges the conversation forward, merging biology, psychology, and philosophy. At the very least, it reminds us that the story of human memory may not be confined to the confines of the brain. It could be written in our very cells, whispering lessons we never knew we had. Germ theory denial. Imagine a world where invisible microbes aren't the culprits behind disease, where the idea that tiny organisms cause sickness is just a story people tell. That's the world of germ theory denial, a stance that challenges what most of us consider science 101. For centuries, humanity battled plagues and epidemics without knowing what caused them. The germ theory, popularized in the 19th century by scientists like Louis Pasteur and Robert Koch, changed all that. But even today, some people reject it, claiming germs aren't the real villains, that disease comes from toxins, bad environments, or even stress. At the heart of this denial is a basic distrust of mainstream science and the institutions that uphold it. Denialists often argue that germs are merely bystanders, that illness arises from internal imbalances or lifestyle choices. Some point fingers at pharmaceutical companies, accusing them of exaggerating germ threats to sell drugs and vaccines. Others reach back to historical figures like Antoine Béchamp, who proposed that tiny microzymas inside the body turn into pathogens only when the body's environment is weak. In this narrative, germs aren't attackers. They're symptoms of a deeper problem. Supporters of this view often present selective evidence to back their claims. They highlight cases where people recover from infections without antibiotics, implying germs weren't the real issue. Historical sanitation efforts and dietary improvements are sometimes framed as proof that germs weren't necessary for disease control. Viral or bacterial cultures shown in labs are dismissed as artificially created or misunderstood, and outbreaks are attributed to poor nutrition, pollution, or emotional stress. Social media amplifies these stories, making it seem like there's a genuine scientific debate when the overwhelming consensus is clear. But stepping back, the critique of germ theory denial is striking. Modern microbiology has mapped countless pathogens, tracked outbreaks, and demonstrated time and again that specific microbes cause specific diseases. Vaccines, antibiotics, and hygiene measures have drastically reduced mortality from diseases like polio, tuberculosis, and smallpox. Denial often ignores controlled experiments where exposure to germs consistently leads to illness. Moreover, blaming lifestyle or environment alone fails to explain why healthy people can suddenly fall ill after exposure to a virus or bacteria. Some alternatives, like holistic or environmental explanations, offer useful lifestyle guidance but don't replace the mechanistic understanding germs provide. The problem arises when denial leads to refusing vaccines, ignoring hygiene, or spreading misinformation, outcomes that are very tangible, very dangerous, and sometimes deadly. In the end, germ theory denial is as much about psychology and culture as it is about science. It thrives on mistrust, selective evidence, and the appeal of a hidden truth narrative. While questioning science is healthy, rejecting a century of rigorous research and observation puts individuals and communities at risk. Understanding germs isn't just about memorizing names or looking under microscopes. It's about recognizing patterns, cause and effect, and the stakes of ignoring reality. The debate isn't purely academic. It shapes public health decisions and personal safety. Germs may be invisible, but the consequences of denial are painfully visible. Terrain theory. Imagine for a moment that germs, viruses, bacteria, all those invisible troublemakers, aren't the main villains in your story of illness. What if the real culprit is the terrain, inside your own body, the environment that either nurtures or fights off disease? That's the pulse of terrain theory, a concept that flips the usual germ-focused narrative on its head. At its core, terrain theory argues that health isn't just about dodging germs. It's about cultivating an internal ecosystem that's inhospitable to disease. Your pH levels, nutrient status, toxin load, immune system strength, these are the soil in which illness either takes root or struggles to survive. Proponents claim that if your terrain is balanced, your body can repel pathogens naturally, making the germs themselves almost irrelevant. It's less about avoiding a cold and more about keeping your body resilient enough that the cold barely stands a chance. Supporters often point to historical figures like Claude Bernard, who emphasized the internal environment, and Antoine Béchamp, who suggested germs are opportunists exploiting a weak host rather than invaders in their own right. They argue that outbreaks of disease often coincide with poor nutrition, high stress, or environmental toxins, not just the presence of pathogens. Some modern studies hint that gut health, chronic inflammation, and vitamin deficiencies play massive roles in susceptibility to infections. The argument is compelling. Strengthen your internal environment, and disease loses its grip. But let's not get carried away. Critics point out a glaring weakness. Terrain theory sometimes downplays the sheer power of certain pathogens. Even the healthiest, terrain, can't always resist diseases like measles or Ebola. The evidence for germ-independent illness prevention is patchy at best. While boosting nutrition and immunity certainly helps, Dismissing microbes entirely ignores centuries of epidemiology showing that viruses and bacteria do cause illness, independent of host condition. Some researchers suggest a synthesis. The body's terrain matters, but germs are still active players. You could call it terrain plus germ theory, an integrated view acknowledging both environment and invaders. Alternative approaches also push the conversation further. Functional medicine and holistic health echo the terrain philosophy, emphasizing diet, sleep, stress management, and detoxification. Meanwhile, conventional medicine relies on vaccines, antibiotics, and sanitation, tools that work directly against pathogens. In practice, people increasingly blend both, maintain a strong internal environment while taking precautions against germs. The controversy isn't about who's right. It's about the balance between empowering the body and acknowledging external threats. In the end, terrain theory challenges us to rethink health from a more personal, proactive angle. It's seductive because it gives agency. If you cultivate your internal terrain, you influence your vulnerability to disease. Even if it doesn't replace germ theory entirely, it invites a more nuanced conversation about wellness, responsibility, and how modern lifestyles might be tilting our terrain into sickness-prone territory. The debate continues, but one thing is clear: disease isn't just about what's out there, it's about the soil within. Vaccines cause autism. You've probably heard the claim that vaccines might trigger autism. It's one of those topics that lights up debates, fuels internet outrage, and makes parents nervous. The idea mostly comes from a controversial study published decades ago that linked the MMR, measles, mumps, rubella, vaccine to autism. Ever since, the notion has stuck in public conversation, even though science keeps raising red flags about it. People latch onto it because autism's causes are still not fully understood, and vaccines are something most kids get, an easy target for worry. At the heart of the claim is the belief that certain ingredients in vaccines, like thimerosal, a mercury-based preservative used in some formulations, could harm the brain and lead to autism spectrum disorders. Some worry that the immune system's response to vaccines triggers neurological changes. Others think the timing of vaccination aligns suspiciously with the age when autism symptoms appear, making the connection feel intuitive to parents and advocates. These core ideas keep the debate alive, especially online, where anecdotal stories carry a lot of emotional weight. Evidence-wise, the original study that started the panic has been thoroughly discredited. Investigations revealed methodological errors, undeclared conflicts of interest, and even falsified data. Large-scale studies across multiple countries have repeatedly found no credible link between vaccines and autism. For example, data from millions of children in Europe, the US, and Asia consistently show vaccinated kids are no more likely to develop autism than unvaccinated kids. Medical authorities, like the CDC, WHO, and the American Academy of Pediatrics back vaccines as safe and emphasize their critical role in preventing serious diseases. Ironically, when people skip vaccines due to autism fears, outbreaks of measles, whooping cough, and other preventable illnesses surge, proving the real-world dangers of vaccine hesitancy. Still, critiques of the mainstream view exist, usually from parents, alternative health advocates, or certain online communities. Many argue that long-term, subtle effects could be missed in studies, or that individual genetic differences might make some children more susceptible. Others insist that vaccines are overused and that natural immunity is undervalued. While these perspectives are worth acknowledging to understand public fears, they haven't produced consistent, reproducible evidence linking vaccines to autism. A more balanced alternative might involve ongoing monitoring, transparency in reporting vaccine ingredients, and better communication between healthcare providers and parents to address concerns without spreading fear. At the end of the day, the overwhelming consensus is that vaccines do not cause autism. The theory persists largely because of early misinformation, emotional anecdotes, and fear of the unknown. Scientific evidence points in the opposite direction, showing vaccines as a cornerstone of public health rather than a risk factor for neurological conditions. Awareness and education remain the best tools for countering myths. So while it's understandable why parents worry, the focus should shift from blaming vaccines to supporting children, funding autism research, and ensuring everyone has access to the life-saving protection vaccines offer. Multiple chemical sensitivity. Imagine walking into a grocery store and suddenly feeling dizzy, your skin tingling, and a pounding headache crashing in. For some people, this isn't paranoia, it's reality. Multiple chemical sensitivity, or MCS, is a condition where everyday chemicals, like perfumes, cleaning products, or even air fresheners, can trigger intense physical reactions. And here's where it gets messy. The medical community still debates whether MCS is a true physical illness or a psychosomatic phenomenon. But dismissing it outright is dangerous. Millions report symptoms that disrupt work, school, and social life. The core of MCS is hypersensitivity. People with MCS aren't reacting to just one chemical. Their reactions can span dozens of everyday substances, often at levels most of us wouldn't even notice. Some researchers argue this is due to an overactive immune system. Others point to neurological wiring gone haywire, where the brain misreads harmless chemical cues as threats. Think of it like your smoke detector going off when someone burns toast. And yet, because symptoms are subjective, headaches, nausea, fatigue, diagnosing MCS is notoriously tricky. There's no universal test, no blood marker, no MRI scan that confirms it, which fuels the skepticism around it. Evidence is scattered but compelling. Case studies show workers exposed to paints or solvents developing severe sensitivities over time. Some experiments suggest repeated low-level chemical exposure can trigger heightened nerve responses in sensitive individuals. Patient narratives echo the same story. Chemicals that barely register to most people can send them into months-long cycles of fatigue, cognitive fog, and pain. Insurance companies and employers may scoff, but for those living it, MCS is terrifyingly real. Even the Environmental Protection Agency acknowledges that chemical sensitivities exist, though they remain cautious in defining the condition as a formal diagnosis. Critics argue MCS is psychosomatic, sometimes labeling it mass hysteria in slow motion. Alternative views suggest anxiety, stress, or prior trauma could amplify perceived chemical reactions. There are even arguments that society's chemical-saturated lifestyle, air pollution, processed foods, synthetic fragrances, could exacerbate both genuine and imagined sensitivities. But here's the twist. Whether it's entirely physical, psychological, or a mix doesn't negate the suffering. Approaches like environmental control, avoiding triggers, and gradual desensitization show practical benefits. Holistic strategies, diet, mindfulness, and air filtration might not cure MCS, but they give patients a fighting chance in a world full of invisible hazards. At the end of the day, multiple chemical sensitivity sits in a gray zone between science, perception, and lived experience. Dismissing it outright is reckless, but over-medicalizing it without clear mechanisms risks wasting resources. What's undeniable is that people are struggling, and society is ill-prepared to accommodate them. From stricter labeling on chemicals to creating trigger-free spaces in workplaces, acknowledging MCS could transform lives. Whether you believe it's all in the head or entirely in the body, the stories are real, the struggles are real, and ignoring them isn't an option. MCS challenges us to rethink how we live among chemicals, pushing the debate far beyond lab results into ethics, accessibility, and basic human dignity. Repressed memory theory. You know those memories that feel buried so deep, it's like they were never yours to begin with? That's where repressed memory theory comes in. The idea is wild. Our minds can shove traumatic experiences so far down that we forget them completely, only for them to pop back up later, sometimes years or decades down the line. It's like your brain has a secret filing system for the stuff it thinks you can't handle. At the heart of this theory is the belief that forgetting can be protective. Imagine witnessing something terrifying or painful, consciously remembering it could be unbearable. So, the mind, in a bizarre form of self-preservation, tucks it away. Later, therapists or certain triggers can supposedly pull these memories back to the surface. People who champion this idea argue that it explains sudden flashbacks, night terrors, or behaviors that seem out of nowhere, all rooted in long-buried trauma. Supporters of repressed memory theory often point to anecdotal evidence. There are countless stories of adults suddenly recalling abuse from childhood or traumatic events previously forgotten. Some clinical cases show patterns where therapy uncovers memories that, once remembered, connect to psychological symptoms people had for years. It's compelling, like a detective story inside your own mind. Neuroscience even hints that extreme stress can affect how memories are stored or recalled, giving a glimmer of biological plausibility. The idea resonates emotionally too. It feels right that our minds would shield us from unbearable pain, only revealing it when we're ready. But here's where it gets messy. Critics argue that these recovered memories aren't always reliable. Memories aren't photographs. They're reconstruction projects that our minds remix constantly. Suggestive therapy techniques, hypnosis, or repeated questioning can accidentally create memories that never happened. The infamous cases in the 80s and 90s, where adults accused relatives based on recovered memories later shown to be false, shook the theory's credibility. Even neuroscientists caution that while the brain can forget trauma, fully repressing and later accurately recalling it is far less straightforward than the theory suggests. Some researchers prefer the idea of ordinary forgetting, combined with trauma-triggered cues rather than complete repression. So where does that leave us? Repressed memory theory straddles a fine line between fascinating psychological insight and risky speculation. It taps into deep fears and hopes about memory, trauma, and self-understanding, but the evidence is far from conclusive. Maybe it's true in some cases, and completely off in others, or maybe our minds are just messier and more suggestible than the theory lets on. Either way, it's a concept that keeps therapists, scientists, and legal systems on their toes, forcing us to ask uncomfortable questions about what we can trust in our own minds. It's a story about memory, trauma, and human vulnerability, one that might never have a tidy ending. Power pose hypothesis. Ever wonder why some people just look confident the second they walk into a room? That's the essence of the power pose idea. Stand like a superhero, hands on hips, chest out, and suddenly you might actually feel more powerful. The claim is simple but bold. Body language doesn't just signal confidence to others. It feeds back into your brain, changing hormone levels, boosting testosterone, lowering cortisol, and making you act more assertively. It's like your body is hacking your own psychology with nothing but posture. The core idea is seductive because it's so actionable. If slouching makes you timid, then striking a dominant pose should, in theory, make you bolder. Amy Cuddy, the psychologist who popularized the idea, suggested that even a brief 2-minute power pose could influence real-world outcomes, interviews, negotiations, or social interactions. It's a neat narrative. Small, deliberate actions can tweak your internal chemistry and shift your confidence instantly. People love it because it's low effort, high reward. Stand like Wonder Woman, and suddenly the world seems a bit more manageable. There's evidence that made this concept explode into the mainstream. Early lab experiments reported measurable changes in testosterone and cortisol, along with self-reported feelings of power after posing. Media coverage turned it into a self-help mantra overnight. Celebrities, motivational speakers, and TED Talks embraced it, turning it into almost a cultural meme. Strike a pose on the room. Some studies claimed behavioral effects too. People were more likely to take risks or assert themselves after power posing. It's intuitive, visually compelling, and almost cinematic in its promise. Posture literally reshapes your brain chemistry. But here's where the controversy hits. Subsequent research struggled to replicate the hormone changes. When bigger, more rigorous studies were run, the dramatic spikes in testosterone and drops in cortisol often vanished. Critics argue that the original experiments were too small or prone to publication bias. Some researchers suggest that feeling more confident may be real, but the physiological mechanism is shaky at best. Others point out that the social context matters. Striking a pose alone in your bedroom might feel empowering, but in a tense boardroom, it could feel awkward or even backfire. Alternative explanations, like placebo effects or self-affirmation, might better account for why people think power poses help. Even with the critique, the power pose hypothesis sparks an important discussion about embodiment and psychology. Whether or not hormones shift dramatically, adopting open, expansive postures can influence mindset and social perception. The key takeaway might not be about magic chemicals, but about self-perception and how small, deliberate acts can prime you for confidence. It's a reminder that our bodies and minds are deeply intertwined, and even symbolic gestures can shift our internal state. So, are power poses the ultimate secret to confidence, or just a flashy placebo? The answer might lie somewhere in between. They're not a miracle switch for power, but they're also more than meaningless theatrics. At the very least, they remind us that sometimes, pretending to be confident is the first step toward actually feeling it, even if the science behind hormone shifts is murkier than the viral TED Talk made it seem. Serotonin Imbalance Theory. You know how sometimes people say depression is just a chemical imbalance? That's mostly what the serotonin imbalance theory is all about. The idea is simple. If your brain doesn't have enough serotonin, a key neurotransmitter, you end up feeling sad, anxious, or generally off. It sounds almost too neat, like blaming a single ingredient when a cake goes wrong. But for decades, this theory has shaped the way mental health is treated, marketed, and understood. At the heart of it, serotonin is this little messenger floating between neurons, whispering, "All is okay," signals. The theory suggests that when those whispers get weak, your mood tanks. Antidepressants, especially SSRIs, are designed to boost these whispers by keeping serotonin around longer in the synapses. The core idea is that tweak the chemistry, and the mind follows. It's appealing because it gives a concrete, measurable handle on something as messy as human emotion. Supporters of this idea point to a few pieces of evidence. SSRIs do help a lot of people feel better, which seems like proof that serotonin levels matter. Brain scans and studies show that people with depression often have altered serotonin activity. Plus, the simplicity of it fits neatly into how the pharmaceutical industry wants to talk about mental health. A pill fixes the imbalance. There's also the genetic angle. Some studies suggest certain serotonin transporter genes are linked to vulnerability to depression, hinting that biology plays a role. But here's where it gets messy. Critics argue that the serotonin story is far from complete. Many people don't respond to SSRIs at all, which throws a wrench into the low serotonin equals depression narrative. Some studies show that serotonin levels in depressed individuals aren't consistently lower than in healthy individuals. It's not a one-size-fits-all chemical issue. Environmental stress, trauma, social context, and even lifestyle massively influence mood. Alternatives like the neuroplasticity model suggest depression is more about how brain circuits adapt, or fail to adapt, over time, rather than just a serotonin deficit. Even some recent meta-analyses hint that the popular imbalance narrative was oversimplified from the start, possibly exaggerated for marketing convenience. Still, the serotonin theory isn't useless. It opened doors to effective treatments and gave millions a language to talk about their struggles without shame. But framing depression purely as a serotonin shortage risks making the problem sound mechanical and individual, ignoring social and psychological dimensions. The controversy now is about nuance. Antidepressants can work, but the reason they work might not be just restoring serotonin. It's a bigger picture of brain chemistry, cognition, and environment all tangled together. So, if you think about it, the serotonin imbalance theory is less a full explanation and more a starting point. It sparks conversation, treatment, and research, but it shouldn't be treated as gospel. Depression isn't just a bottle of pills away, it's a complex, living story inside each brain, shaped by biology, experience, and the world we live in. Understanding that complexity doesn't make treatment hopeless, it makes it more honest, flexible, and ultimately human. Psychic phenomena research. You ever get the feeling someone's watching you, or dream of something that later happens? That weird gut instinct. Some call it psychic phenomena. For decades, researchers have tried to figure out whether these experiences are just tricks of the mind, or if there's something genuinely unexplained going on. Psychic phenomena isn't just about fortune tellers or Hollywood plots. It's about human perception stretching beyond the usual limits. At the heart of it are concepts like telepathy, precognition, psychokinesis, and clairvoyance. Telepathy suggests people can share thoughts without speaking, while precognition hints that some can sense the future. Psychokinesis, the classic "move objects with your mind" idea, stretches belief further, and clairvoyance claims people can see events or objects far away without conventional senses. These aren't just fun stories. They're persistent human experiences across cultures and centuries, appearing in everything from tribal folklore to modern reports of déjà vu and intuition that feels oddly accurate. Evidence is where the debate heats up. Experiments at places like the Princeton Engineering Anomalies Research Lab tried to detect telepathy through card-guessing games, with some studies showing results just beyond random chance. In the 1970s, psychologist Daryl Bain conducted experiments suggesting that people could anticipate events before they happened, though skeptics pointed out flaws in methodology and statistical handling. There are anecdotal accounts too. Soldiers sensing danger before it happens, people predicting accidents, or famous instances of psychic detectives contributing clues in criminal cases. It's tempting to think there's a hidden layer to reality, but the scientific rigor often wavers, and replication remains a huge issue. Critics are quick to challenge every claim. Skeptics argue that selective memory, coincidence, and cognitive biases explain most psychic phenomena. Confirmation bias makes people remember hits and forget misses. The brain excels at pattern recognition, even where none exists. Controlled experiments often fail to replicate flashy results, suggesting the mind may be tricking itself more than the universe bending its rules. Some alternatives even suggest subtle environmental cues or social signals could explain seemingly psychic events. And neuroscience points out that intuition can emerge from unconscious processing rather than mystical forces. Yet, dismissing everything outright might be too extreme. The experiences themselves are real, even if the explanations are murky. Ultimately, psychic phenomena research sits in a gray zone. It's a mix of tantalizing hints and frustrating uncertainty. On one hand, it challenges our understanding of consciousness and reality. On the other, it tests the patience of the scientific method. Whether these experiences are truly paranormal, a quirk of the human mind, or a little of both, they spark curiosity, debate, and sometimes disbelief. For now, the conversation isn't settled, and maybe that's part of the point, pushing us to question what we know about ourselves and the unseen possibilities around us. Left brain, right brain myth. You've probably heard someone say, "I'm totally a right brain person," or "left brain thinkers are all logic and numbers." It's catchy, it feels true, and it's everywhere, from motivational posters to dating apps. But here's the thing, it's mostly a myth. The idea that one side of your brain rigidly controls creativity and the other rules logic is oversimplified, misleading, and just plain wrong in the way most people imagine it. The origin of this myth traces back to the 1960s, thanks to split brain studies. Neuroscientists like Roger Sperry and Michael Gazzaniga studied patients whose corpus callosum, the bridge between the brain's hemispheres, was severed to control severe epilepsy. They noticed that each hemisphere could process information independently in some situations, leading to the tempting idea that the left brain handles logic, language, and analysis, while the right handles art, intuition, and emotion. People ran with it, and soon it became a cultural shorthand for personality types and learning styles. But real science tells a more complicated story. Modern neuroimaging shows that both hemispheres are active in almost every task. Language, for example, is mostly left lateralized, yes, but understanding metaphor, humor, or even sarcasm lights up areas in both hemispheres. Creativity isn't tucked neatly into the right side either. Composing music, painting, or problem-solving requires a dynamic network that spans the whole brain. There isn't a switch you can flip to suddenly become a right brain thinker. Our brains are messy, interconnected, and surprisingly adaptable. Some studies even suggest that framing people as left-brained or right-brained could limit potential. Labeling someone as analytical might discourage them from exploring artistic pursuits, and vice versa. It's not just a harmless myth. It can subtly shape educational choices, career paths, and self-perception. The appeal is understandable. We love simple stories, clean divisions, and the sense that our traits are pre-written in our brains. But that simplicity comes at a cost. It's scientifically inaccurate and psychologically constraining. Critics of the myth argue for a more network-based understanding of cognition. Instead of hemispheres dictating who we are, it's the interaction of distributed brain regions that matters. Cognitive flexibility, emotional intelligence, problem-solving, and creativity are products of these cross-hemisphere conversations, not single-sided dominances. Brain training and neuroplasticity further reinforce this. You can strengthen skills and abilities regardless of which side you think you're on. Educational programs are increasingly moving toward integrated learning that challenges both analytical and creative thinking simultaneously, which aligns with how brains actually work. At the end of the day, the left brain/right brain story is seductive, but it's a narrative, not reality. Your creativity, logic, humor, and intuition don't live on separate sides of your skull. They're woven together in a dynamic, networked brain. Believing otherwise can be limiting, but embracing the messiness? That's where the real potential lies. So next time someone calls themselves a right-brainer, smile and remember, it's not about which side dominates. It's about how the whole brain collaborates. Science doesn't have to be boring or rigid. It can challenge the stories we've been telling ourselves, and sometimes, debunking a myth makes life more interesting, not less. Chemtrail Conspiracy Theory. You ever look up on a clear day and see those long, white streaks cutting across the sky and wonder, are planes just flying, or are they secretly dumping something on us? That's where the chemtrail conspiracy kicks in. Unlike ordinary condensation trails that vanish quickly, Chemtrail believers say some trails hang around for hours, forming patterns, and that's supposedly the smoking gun for a secret government plot. It's one of those stories that makes you squint at the sky and rethink your trust in modern aviation. The heart of the theory is pretty wild. People claim that governments, sometimes in collusion with big corporations, are dispersing chemicals from planes for purposes that range from weather control and climate engineering to mind control and population manipulation. Some even suggest it's a huge secret experiment in geoengineering, altering rainfall or temperature to suit political or economic agendas. To them, every jet leaving a lingering trail is a brushstroke in a hidden global plan, and the sky itself is the canvas of covert operations. Supporters of the theory point to a few oddities as proof. They note that some trails persist longer than a normal contrail should, sometimes spreading across the sky in grids or lines, rather than dissipating quickly. Some cite laboratory tests claiming to find unusual metals like barium, aluminum, or strontium in rainwater or soil samples, hinting that these substances are being deliberately released. Eyewitness photos and videos of planes leaving intricate patterns also get passed around online like treasure maps, suggesting intentionality rather than random atmospheric effects. And the timing of certain trails near large cities or during political events fuels suspicions that it's all orchestrated rather than coincidental. But when you dig deeper, the evidence starts to wobble. Scientists explain that contrail persistence depends on air temperature, humidity, and altitude, which is why some trails linger while others vanish. The metals found in environmental tests often exist naturally or come from industrial pollution unrelated to planes. Atmospheric scientists argue that patterns in the sky are just the result of flight paths intersecting and wind spreading the vapor. Even photos and videos can be misleading. Light, perspective, and the human brain's love for patterns can make ordinary contrails look intentional. Essentially, the science behind normal contrails accounts for almost all the claimed anomalies without invoking a secret global scheme. Still, the chemtrail theory thrives because it taps into a deeper mistrust of governments, corporations, and opaque systems. It's a story with clear villains and hidden forces, and that narrative is gripping. While there's no verifiable proof that planes are deliberately spraying harmful chemicals as part of a global plan, the debate highlights a real cultural phenomenon: people questioning authority and wanting to see what's really happening above their heads. Whether you buy into it or not, looking at the sky now comes with a little extra curiosity, a healthy dose of skepticism, and maybe a tiny pinch of paranoia, which, let's be honest, keeps life interesting. Anthropogenic global warming. You ever stop and think about how humans have flipped the planet's thermostat without even asking nature? That's the reality we're staring at. Our activities, from burning fossil fuels to chopping down forests, are turning the Earth into a slow-cooking experiment. It's not some distant sci-fi. The effects are real, tangible, and creeping into every corner of our lives. The core of this crisis is simple: greenhouse gases. Carbon dioxide, methane, nitrous oxide, they trap heat in the atmosphere like a thick blanket. Industrial machinery, cars, power plants, even our diet choices pump these gases relentlessly. Every time we choose convenience over conservation, the climate clock ticks louder. And it's not just numbers on a chart. These emissions are reshaping weather patterns, melting ice caps, and shifting ecosystems faster than many species can adapt. Look at the evidence. Arctic sea ice is shrinking year by year, glaciers are retreating, and extreme weather events are multiplying. Scientists aren't whispering warnings anymore. They're screaming them. Hurricanes pack more punch, wildfires spread like brush fires on steroids, and droughts are now rewriting agricultural maps. It's a domino effect. Oceans are warming and acidifying, coral reefs are bleaching, and entire marine populations are collapsing. And yet, some still argue that this is just natural cycles, ignoring decades of atmospheric measurements that point straight to human fingerprints. But here's where it gets contentious. Critics push back, saying that climate models can't be 100% accurate, that technological innovation could bail us out, or that geoengineering might reverse the damage. There's some truth in questioning models. They're not crystal balls, but dismissing decades of data as mere speculation is dangerous. Alternatives like renewable energy, reforestation, and carbon capture aren't perfect fixes, but they are steps toward not leaving a scorched earth for the next generation. The debate isn't whether humans influence the climate. It's how far we're willing to go to change our behavior before the tipping point becomes irreversible. So what's the takeaway? Anthropogenic global warming isn't a theory. It's a messy, inconvenient fact. The planet doesn't negotiate. Rising seas, collapsing ecosystems, and unpredictable weather are sending a clear message. And the clock is ticking. Change requires more than acknowledging the problem. It demands action, innovation, and, most importantly, a willingness to rethink our lifestyles and priorities. We're at a crossroads. Continue down the path of denial and delayed action, or step up and redefine our relationship with the planet. Future generations won't thank us for ignoring the heat. They'll inherit it. Clathrate Gun Hypothesis. Imagine a ticking time bomb beneath the ocean floor, frozen in icy cages, just waiting for the right trigger. That's essentially the heart of the Clathrate Gun Hypothesis. This idea suggests that methane, locked inside these icy structures called clathrates, could suddenly burst into the atmosphere, supercharging global warming almost overnight. It's like nature holding a match near a gas leak, terrifying but fascinating. At its core, clathrates are compounds where methane molecules are trapped inside a lattice of water ice. They form under high pressure and low temperature, mostly on continental slopes and beneath permafrost. The gun in this hypothesis comes from the idea that a warming Earth could destabilize these clathrates. As ocean temperatures creep up or permafrost thaws, the cages could collapse, releasing massive amounts of methane, a greenhouse gas far more potent than CO2 in the short term. Some scientists argue this sudden release could trigger abrupt climate changes, even tipping the planet into scenarios we've only glimpsed in ancient mass extinctions. Evidence supporting this isn't just theoretical. Geological records hint at massive methane releases coinciding with past rapid warming events. Take the Paleocene thermal maximum, PTM, roughly 55 million years ago. Temperatures jumped by 5 to 8 degrees Celsius in just a few thousand years, and a spike in carbon isotopes suggests a huge methane release, potentially from destabilized clathrates. Today, satellite measurements and deep-sea expeditions detect methane plumes rising from the seafloor in places like the East Siberian Arctic Shelf, where warming is especially rapid. Ice cores, sediment samples, and methane flux studies all feed into the idea that this isn't just a relic of the past. It could happen again. But the hypothesis isn't without critics. For one, the timing and scale are debated. Some researchers argue that methane hydrates are more stable than the gun analogy implies, and that gradual release over centuries, not sudden bursts, is more likely. Others point out that a lot of released methane gets oxidized in seawater before reaching the atmosphere, damping the impact. There's also the possibility of alternative explanations for ancient warming events, such as volcanic CO2 emissions or shifts in ocean circulation, which could muddy the waters of blame. And while modern methane plumes exist, translating these localized emissions into a global catastrophe is far from straightforward. Still, the Clathrate Gun Hypothesis matters because it forces us to confront an uncomfortable reality. The climate system has triggers we may barely understand. Even if a sudden methane burst is improbable, The existence of such a mechanism reminds us how interconnected temperature, ocean chemistry, and greenhouse gases are. It's a reminder that human-driven warming doesn't happen in a vacuum. Ancient forces lurk beneath, capable of amplifying changes in ways that could surprise us. In the end, the Clathrate Gun Hypothesis isn't just about frozen methane or scary science headlines. It's a lens for thinking about tipping points, feedback loops, and the fragility of Earth's climate balance. Whether it detonates in the future or remains a relic of geological history, it challenges us to look beneath the surface, literally and figuratively, and consider how much we really know about the planet's hidden power. Plate tectonics. Imagine Earth as a giant jigsaw puzzle, each piece moving ever so slowly but relentlessly. That's the core of plate tectonics. Our planet's surface isn't one solid shell, but a mosaic of plates, drifting, colliding, and pulling apart. This theory flips the way we've historically thought about the ground beneath our feet. It's not static, it's alive, restless, and sometimes catastrophic. Volcanic eruptions, earthquakes, even the creation of mountains, these aren't random acts of nature, but the direct consequence of the invisible dance of tectonic plates. At its heart, plate tectonics is about motion. The lithosphere, the outer layer of Earth, is broken into massive plates that float atop the semi-fluid asthenosphere. When plates converge, continents buckle and mountains rise. When they diverge, new crust is born from molten rock. And then, there are transformed boundaries, where plates slide past each other, storing tension until it's violently released as earthquakes. It's a system driven by convection currents deep within the mantle, a heat engine that moves continents in a geologic game of bumper cars. The scale is hard to grasp. Plates move mere centimeters a year, but over millions of years, that's enough to rewrite the face of the planet entirely. The evidence supporting this theory is compelling and multifaceted. Look at the puzzle piece fit of South America and Africa, or the matching fossil records across oceans. Magnetic stripes in the ocean floor record the history of seafloor spreading. Earthquakes and volcanic activity trace predictable paths along plate boundaries. Even satellite technology now allows us to measure plate motion directly, turning theory into observable fact. These lines of evidence converge to paint a picture of a dynamic planet that's constantly reshaping itself, contradicting centuries of belief that Earth is immutable and stable. Yet, like any scientific theory, plate tectonics isn't immune to debate. Some argue that mantle convection alone doesn't fully explain plate movement or the initiation of subduction zones. Others propose alternative mechanisms, like plume tectonics, suggesting hotspots may play a larger role in driving continental drift than previously thought. While these critiques don't dismantle the core theory, they highlight that the planet's inner workings are immensely complex, and our understanding is still evolving. Even the seemingly settled idea of plate motion has nuances, exceptions, and unanswered questions that keep geologists busy and occasionally squabbling. Ultimately, embracing plate tectonics changes the way we see Earth. It transforms the planet from a static backdrop into an active participant in the story of life. Mountains are not eternal. Coastlines are temporary. Continents drift like ships on a molten sea. The theory reminds us that our world is constantly in flux, that the ground beneath us has a history written in motion, pressure, and fire. It's controversial not because it's wrong, but because it challenges our instinct to see the world as fixed and predictable. Understanding it isn't just academic, it's a perspective shift, a way to respect the restless energy that shapes everything from the soil underfoot to the skies above. Hollow Earth. Ever wondered if the world we walk on is just a shell, hiding entire civilizations below? The Hollow Earth theory isn't just sci-fi fodder. It has roots stretching back centuries. Early thinkers like Edmund Halley, yes, the comic guy, imagined the Earth as layers with empty spaces inside. Today, it sparks a mix of curiosity and eyebrow-raising skepticism. The core idea is wild yet simple. Earth isn't solid all the way through. Instead, it's more like a hollow sphere with massive internal cavities, inner suns, and maybe even hidden ecosystems or civilizations thriving beneath our feet. Some versions of the theory suggest entrances at the poles, while others propose vast tunnels connecting hidden realms. Advocates argue that the poles are gateways, foggy and unmapped, hiding secrets mainstream science refuses to acknowledge. Supporters point to historical maps, legends, and certain unexplained phenomena. Ancient myths describe underground worlds, think Agartha or Shambhala, that mirror the hollow earth idea. Explorers, like Admiral Byrd, allegedly reported strange magnetic anomalies and warm areas beyond the polar ice, which some interpret as signs of entrances. Earthquakes and volcanic eruptions, surprisingly, are sometimes cited as evidence that massive hollow spaces shift or collapse inside the planet. Even some UFO enthusiasts argue that extraterrestrials use these hidden realms as secret bases. But the theory faces heavy critique. Physics, geology, and satellite data all insist Earth's interior is mostly solid with a molten core. Gravity, seismology, and the way tectonic plates move don't leave room for massive hollow cavities. The math just doesn't add up. Some so-called evidence, like Byrd's diary entries or polar anomalies, often get twisted or exaggerated. Critics also point out that myths of underground civilizations can be metaphorical rather than literal, reflecting spiritual ideas or moral lessons rather than secret continents. Modern exploration and polar satellites would likely have spotted any sizable openings by now. Alternatives suggest that the hollow earth concept might actually be a metaphor for hidden knowledge, unseen parts of the human psyche, or untapped natural resources. Others propose that tales of inner worlds inspired science fiction rather than science fact, influencing writers from Jules Verne to H.P. Lovecraft, while keeping the imagination alive for generations. Still, the allure remains. The hollow earth theory scratches a primal itch, to believe there's more to our planet than meets the eye. It challenges official narratives and encourages questioning what we think we know about our own world. Even if it's scientifically shaky, it's a mental playground, a controversial lens through which to examine history, myth, and the unknown. Maybe it's less about proving hollowness and more about reminding us that the Earth, much like our curiosity, might have layers we haven't fully explored yet. Catastrophism. Picture this. The Earth isn't just this slow, predictable clockwork. Sometimes it explodes, crashes, or shakes in ways that rewrite history overnight. That's catastrophism, a theory that flips the slow and steady idea of change on its head. Instead of mountains forming inch by inch over eons, catastrophism says sudden, violent events can sculpt landscapes in a heartbeat. Think floods, earthquakes, volcanoes, asteroid strikes. The Earth has a dark, dramatic side, and catastrophism insists we pay attention to it. The core idea here is simple but radical. History is not always gradual. Massive, sudden events, catastrophes, shape the planet. Entire ecosystems vanish, species disappear, coastlines redraw themselves, and entire civilizations are forced to start over. It's a challenge to the slow and steady uniformitarian view, which claims that the same tiny forces we see today, erosion, sedimentation, weathering, explain everything given enough time. Catastrophism dares to say, nope. Sometimes the rules change fast, and the impact is enormous. Evidence for catastrophism is surprisingly compelling. Look at the geological record. Layers of sediment that seem to appear overnight, sudden mass extinctions in the fossil record, massive craters hinting at asteroid collisions, and volcanic ash layers that blanket continents. Even ice cores tell a story of abrupt climate swings. Take the asteroid impact 66 million years ago that wiped out the dinosaurs. One moment, the planet is thriving. The next, a cataclysm changes the entire evolutionary path. Flood legends across cultures? Some scientists think they might be distorted memories of real, massive floods. Catastrophism isn't just speculation. It's written into rocks, ice, and fossils if you know how to read it. Of course, this view isn't without critics. Many scientists argue that catastrophism alone can't explain the deep, persistent patterns we see in Earth's history. Slow processes matter too, and some argue catastrophes are dramatic but rare, making them less central than they seem. Others propose a middle path. Yes, the Earth is shaped by gradual forces, but punctuated by rare, violent events that accelerate change. Think of it as a slow movie with occasional plot twists that leave everyone gasping. It's controversial because it forces us to reconsider the reliability of normal time scales and question whether our assumptions about stability are just comforting illusions. So what's the takeaway? Catastrophism reminds us that the Earth is not a predictable machine. It's a place of sudden shocks and dramatic turns. Whether or not you buy into it fully, the theory forces a fresh lens, one where history is written not only in quiet whispers, but in explosive, unforgettable moments. We might not know exactly when the next event will hit, but catastrophism teaches us to respect the unpredictable power of the planet we call home. In the end, it's less about proving one side right and more about accepting that sometimes change isn't polite or gradual, it's violent, fast, and utterly transformative. Abiotic Oil Theory. You know how everyone's been taught that oil is basically dinosaur juice trapped underground for millions of years? Well, the abiotic oil theory throws that whole idea a curveball. This theory suggests that petroleum isn't just some leftover organic sludge. It might actually be generated deep inside the earth from carbon deposits, completely independent of ancient life. It's like finding out the magic trick you believed in forever might actually be a completely different trick. The idea is that the Earth's mantle, a layer way below the crust, contains carbon compounds that under extreme heat and pressure can form hydrocarbons. Yes, real oil. These hydrocarbons then migrate upwards through the rock layers and collect in reservoirs, just like conventional oil. It's a simple concept, but it flips the script on what we think about oil being a finite, decaying resource. If this is true, oil could potentially be more abundant than the textbooks tell us, which is exactly why this theory sparks both fascination and heated debate. Supporters of abiotic oil point to some intriguing evidence. First, there are reports of hydrocarbons in places where no organic matter existed, like certain igneous rocks or deep mantle deposits. Some Russian studies in the mid-20th century even claimed to produce hydrocarbons in lab conditions from carbon, iron oxide, and water under extreme heat, mimicking Earth's interior. Then there's the weird phenomenon of oil appearing in huge amounts in regions geologists didn't expect it, hinting that organic decay might not be the only source. And let's not forget methane, which pops up in extreme environments like deep-sea vents or in outer space, places no dinosaurs ever roamed. That's the kind of stuff that keeps scientists arguing late into the night. But of course, not everyone's buying it. Critics argue the theory doesn't explain the huge chemical fingerprints of organic material found in almost all oil samples. Most oil seems packed with biomarkers pointing directly to plants and ancient microbes. Plus, while lab experiments can make hydrocarbons from inorganic sources, scaling that up to explain the massive reservoirs we extract today is another story. There's also the point that oil is rarely, if ever, found pure in deep mantle rocks. It tends to be tied up in sedimentary layers, which fits neatly with the biological origin story. And let's be honest, the idea that Earth keeps pumping out oil indefinitely doesn't exactly help climate change arguments, so there's definitely an incentive to be skeptical. Even with the controversy, the Abiotic Oil Theory forces us to think differently about energy and geology. It's a reminder that the Earth is full of surprises and that what seems settled science might just be the popular story, not the only story. Whether you end up siding with traditional geologists or the rebels who believe oil might just be Earth's secret trick, exploring the idea expands your perspective. And in a world running low on fossil fuels, questioning whether oil is truly finite or might be more of a natural process is more than just an academic exercise. It's a conversation with potentially huge implications for how we see energy, economy, and even our planet itself. Technological singularity. Imagine a moment in history when machines don't just help us, they surpass us, thinking faster, smarter, and maybe even in ways we can't predict. That's the technological singularity. It's not just sci-fi chatter. It's the idea that artificial intelligence could reach a point where it improves itself endlessly, spiraling past human control. Some call it the ultimate evolution of intelligence. Others warn it's a ticking bomb for humanity. At the heart of it, singularity is about acceleration. AI is learning at breakneck speeds. Algorithms now can write, create, strategize, and even mimic human intuition. Combine this with quantum computing or other breakthrough tech, and you're looking at systems that could redesign themselves, solve problems we can't even conceive, or make decisions with a logic we may never understand. The core idea isn't just smarter computers. It's a tipping point where human intelligence might become irrelevant, at least in comparison. Supporters argue that the signs are already here. Look at GPT models capable of writing essays, coding programs, or analyzing complex data patterns. DeepMind's AI mastered protein folding, something that stumped human scientists for decades. Autonomous systems in finance, logistics, and medicine are making decisions faster and often more accurately than humans. The trend is exponential. Moore's law may have slowed, but AI development curves are anything but linear. Experts like Ray Kurzweil predict this tipping point within a few decades, suggesting that once AI can improve itself, the changes will happen at lightning speed, leaving us scrambling to keep up. But it's not all smooth sailing. Critics point out that intelligence isn't just about processing power, it's about context, empathy, morality, and unpredictability. Machines may be fast, but can they truly grasp the messy, irrational human world? There's also the risk of control. If a superintelligent AI prioritizes goals we don't understand or can't influence, consequences could be catastrophic, from economic collapse to existential threats. Some suggest regulated slow development, hybrid human-AI partnerships, or embedding ethical frameworks into AI. But even these solutions have flaws, because no code can perfectly anticipate the chaos of real-world consequences. Then, there's the philosophical side. Are we ready to witness our own obsolescence, even if it's in a benevolent form? Could AI, in surpassing human intelligence, redefine what it means to be human? Some argue singularity isn't inevitable. It's a projection based on our obsession with speed and optimization. Others see it as an unstoppable force, a horizon we can glimpse but never touch without consequences. Either way, it forces us to question who controls the future, us or the machines we've created. So, the technological singularity sits at the crossroads of awe and fear. It promises breakthroughs that could cure diseases, end scarcity, or unlock mysteries of the universe, but also raises alarms about autonomy, ethics, and survival. The debate isn't just about technology. It's about humanity's place in a rapidly changing world. Whether it arrives as a savior, a disruptor, or a warning, the singularity challenges us to confront the ultimate question: can we guide our creations, or will they guide us? Brain uploading. Imagine being able to step out of your body, like leaving your messy apartment, and moving your mind into a perfectly coded digital world. Sounds like sci-fi, right? But brain uploading, or mind uploading, is not just a fantasy. It's the idea that one day we could scan every neuron, every synapse, every flicker of electrical activity in our brains and replicate it in a computer. Your thoughts, memories, personality, entirely digital, potentially immortal. At its core, brain uploading rests on two bold assumptions. First, that consciousness is essentially information. If your mind is a complex pattern of signals, theoretically, those signals could be copied. Second, that technology will eventually be precise enough to map every neural detail. Think of it as creating a perfect virtual twin. Not just a copy, but you, with all your quirks, memories, fears, and humor intact. Supporters point to rapid advances in neuroscience and computing. We're already simulating tiny neural networks, like the nematode worm C. elegans, in painstaking detail. AI is learning to mimic aspects of human cognition. Futurists argue that once we fully understand how neurons encode thought, nothing stands in the way of digitizing a mind. Imagine escaping the biological limits of disease, aging, and death. Your consciousness could be backed up, transferred, even shared across multiple bodies or virtual worlds. Immortality, at least in some form, suddenly seems less impossible. But critics have plenty to argue. Mapping every neuron might be feasible someday, but is that really you? If your memories and patterns are copied into a machine, is that a continuation of your consciousness or just a convincing clone? Philosophers call this the ship of Theseus problem. Replace every part of a thing. Is it still the same thing? There's also the messy moral side. Who owns a digital mind? Could corporations monetize you? Hack your consciousness? And the idea of living in a purely digital existence raises questions about identity, emotions, and meaning. Could a brain in a machine truly experience joy or love, or is it just running simulations of emotions? Alternatives to full uploading might feel less extreme, but still transformative. Neural enhancement, memory recording, or hybrid brain-computer interfaces could let humans boost cognition without fully leaving the biological body. These methods offer a middle ground, extended life and intelligence without the radical leap into full digital existence. Whether brain uploading becomes reality or stays science fiction, it forces us to rethink what it means to be human. Is consciousness tied to flesh, or is it just data? Are we prepared for a world where your mind could outlive your body, or even be copied multiple times? The debate isn't just about technology. It's about identity, ethics, and the future of existence itself. Brain uploading pushes the boundaries of life, death, and the essence of self in ways that feel exhilarating, terrifying, and irresistibly controversial all at once. CRISPR designer babies. Imagine a world where parents can choose not just the eye color or height of their child, but also the very blueprint of who they will become. CRISPR, a gene editing tool that seems straight out of sci-fi, makes this a real possibility. It's precise, fast, and powerful, allowing scientists to snip and tweak DNA with a level of control we've never seen before. But with this power comes a storm of questions about ethics, inequality, and what it truly means to be human. The core idea behind CRISPR designer babies is simple yet profound. Eliminate genetic diseases and enhance desirable traits before birth. Conditions like cystic fibrosis, sickle cell anemia, and muscular dystrophy could be erased from a family line entirely. But beyond health, the technology could allow tweaks for intelligence, athletic ability, or even personality traits. Essentially, parents could become architects of the next generation, shaping humans before they even take their first breath. Evidence supporting this isn't just hypothetical. In 2018, a Chinese scientist edited the genomes of twin embryos to resist HIV, sparking global outrage. This experiment highlighted both the potential and the danger. Yes, gene editing can prevent serious diseases, but it can also go wrong. Unintended mutations, off-target effects, and long-term consequences we can't yet predict remain huge risks. Studies on animals show promise, but translating that safely to humans is still uncertain. Ethicists warn that even minor errors could create lifelong problems that ripple across generations. Critics argue that the push toward designer babies risks a slippery slope into genetic inequality. If only the wealthy can afford enhancements, we might create a new class of genetically privileged humans. There's also the psychological impact on children, who might feel more like projects than people. Some suggest alternative approaches, improving overall healthcare, nutrition, and access to education could enhance life outcomes without touching genes. Others recommend strict limits, allowing CRISPR only for disease prevention, not cosmetic or performance traits. Closing this debate isn't easy, because we're not just talking about science, we're talking about society, morality, and identity. CRISPR designer babies present a paradox, a tool that can save lives, but also redefine what it means to be human. How we choose to use it will shape the next century of human evolution, for better or worse. The discussion isn't about whether we can do it anymore, it's about whether we should, and under what rules. In the end, it's a mirror reflecting both our highest hopes and deepest fears as a species. Longevity escape velocity. Imagine a world where aging isn't a sentence, but a challenge we might constantly outpace. Longevity escape velocity, LED, is that wild idea. If science progresses fast enough, for every year you age, medicine can extend your life by more than a year. You'd be, in essence, outrunning death, not forever, maybe, but long enough to see technologies keep catching up. Sounds like sci-fi? Maybe, but it's inching closer to reality. The core concept is deceptively simple. Our bodies deteriorate over time. Cells mutate, organs fail, tissues accumulate damage. Traditional medicine slows the process in bits and pieces. Statins for the heart, dialysis for kidneys, cancer therapies here and there. LED proposes a bigger picture, tackle aging itself. Repair, rejuvenate, replace, keep the biological clock from ticking faster than our interventions. If researchers can extend life faster than the clock is running, you hit escape velocity. It's like keeping a rocket accelerating just enough to break free of Earth's gravity, except the Earth is death. Supporters point to exponential gains in biotech and AI-driven medicine. Senolytics, drugs that clear senescent cells, have shown the potential to reverse tissue aging in mice. Gene editing, like CRISPR, could correct cellular errors before they snowball. Advanced organ regeneration and artificial organs are no longer the stuff of Marvel. Bioengineered hearts and livers are being tested. The argument is simple: progress compounds. A therapy today buys a few years. By the time you need the next, new therapies might extend your life even further. One day, maybe, each birthday just resets a race you're already winning. But critics are quick to cool the hype. Science is messy, and humans aren't mice. Senolytics don't guarantee decades of extra life. CRISPR may fix one problem while creating another. Some argue LED is overly optimistic, ignoring social, economic, and ethical barriers. If only the wealthy can reach escape velocity, do we accelerate inequality along with our lifespans? And let's not forget the law of unintended consequences. A world where people live hundreds of years could break economies, environmental balance, and social systems in ways we can't yet predict. Others propose alternatives that might be more achievable. Focus on healthy aging through lifestyle, nutrition, and preventive medicine. Not glamorous, not revolutionary, but arguably more practical. Still, the allure of LED is irresistible. It frames aging as a technical problem rather than an inevitable tragedy. Even partial progress could radically reshape how we view our lives, buying decades to experience more, create more, and maybe redefine what it even means to grow old. Whether or not full escape velocity is achievable, the pursuit forces us to confront uncomfortable questions about longevity, fairness, and ambition. It's messy, controversial, and thrilling, a scientific gamble with humanity itself as the stake. In the end, LED challenges a fundamental narrative. Aging isn't destiny. It might just be a puzzle we haven't solved yet. We may not live forever, but the closer we get, the more radical our relationship with time, health, and life itself becomes. And that, in itself, is a revolution worth watching. Geoengineering climate control. The idea of taking control of the planet's thermostat isn't just science fiction anymore. It's happening in labs, boardrooms, and policy debates. Geoengineering, the deliberate manipulation of Earth's climate systems, promises a bold shortcut to slow or reverse global warming. Imagine giant mirrors in space, fleets of ships spraying sulfur into the atmosphere, or chemicals altering clouds to reflect sunlight. Sounds like a high-stakes sci-fi plot, right? But for many, it's the looming reality of desperation as temperatures climb, ice caps melt, and wildfires rage. At the core of geoengineering, there are two main strategies. One is solar radiation management, SRM, essentially reflecting sunlight back into space to cool the planet temporarily. Think of it as a planetary sunshade. The other is carbon dioxide removal, CDR, which tackles the root cause, excess greenhouse gases. Techniques range from massive tree planting and biochar in soils to experimental methods like ocean fertilization to spark carbon-absorbing plankton blooms. Both aim to bend the climate curve, but they come with very different timelines and risks. Proponents argue that geoengineering could buy humanity precious time. Rising global temperatures aren't just numbers. They mean droughts that wipe out crops, storms that flatten cities, and species disappearing before we even notice. SRM can act almost instantly, potentially dropping temperatures in a matter of months, while CDR offers longer-term solutions that, if scaled, could pull us back from the brink. Some studies show that even small-scale SRM interventions could shave off a few degrees of global warming, giving ecosystems and societies a breather. For CDR, modeling suggests it could eventually counteract decades of carbon emissions if pursued aggressively enough. It's an alluring promise: control, precision, and a fast lane out of climate chaos. But the critics are loud and numerous. The moral hazard is glaring. Relying on geoengineering might make governments and corporations complacent about reducing emissions. SRM doesn't address ocean acidification, so we might fix one problem while deepening another. There's also a terrifying political angle. Who decides how much sunlight gets reflected? A misstep in one region could trigger droughts in another, or shift monsoon patterns unpredictably. CDR, meanwhile, is expensive, slow, and resource-intensive, and large-scale experiments could have unforeseen ecological consequences. And yet, the debate continues: can humanity really afford to ignore a potential safety net, even if it's imperfect? So where does this leave us? Geoengineering isn't a magic bullet, but it's an idea whose time may be coming whether we like it or not. It forces a hard conversation about responsibility, risk, and urgency. Could we use it wisely, in tandem with aggressive emissions cuts, renewable energy expansion, and conservation efforts? Or is it the ultimate gamble, a hubristic attempt to play God with Earth systems? The truth is, while science may give us the tools, society has to decide whether to reach for them, and if we do, how to ensure that a desperate fix doesn't spiral into a planetary-scale catastrophe. Behavioral genetics. Imagine a world where your quirks, your fears, even your sense of humor, could be traced back to tiny chemical sequences in your DNA. Behavioral genetics dives straight into that idea. What parts of us are coded in our genes, and which are shaped by life around us? It's the science of trying to decode why we behave the way we do, without sugarcoating or pretending it's all nurture or all nature. At its heart, this field asks bold questions. Are impulsive people born that way, or are they sculpted by their environment? Can mental illnesses, like depression or ADHD, be linked to specific genetic markers? Studies of twins and adoptees provide the clearest glimpses. Identical twins, even when raised apart, often show uncanny similarities: how they laugh, how they react under stress, even career choices. Meanwhile, adoption studies tease apart genes from upbringing. Children sometimes carry traits more like their biological parents than the ones raising them. It's a powerful hint that our behavior isn't just a product of circumstance. Evidence piles up for modern genomics too. Genome-wide association studies, GWAS, are mapping traits to hundreds of genes, revealing subtle but significant patterns. Researchers have found correlations between genetic variants and traits like aggression, empathy, risk-taking, and even political orientation. Animal studies reinforce this. Selective breeding in mice or fruit flies can exaggerate behaviors over generations, demonstrating that behavior can indeed be inherited. But here's the kicker: no single gene dictates a personality. It's always a complex symphony of many genes interacting, often with environmental triggers acting as conductors. But it's not all neat and scientific. Critics argue behavioral genetics can slip into dangerous territory. There's the specter of genetic determinism, the idea that if a trait is genetic, it's fixed. History reminds us this thinking can fuel discrimination or justify social inequality. Even modern science grapples with this. Genes might nudge behavior, but they rarely dictate it. Social context, upbringing, trauma, and personal choices still shape outcomes. Some scholars suggest focusing on epigenetics, how experiences can turn genes on or off, as a more nuanced alternative, blending biology and environment instead of elevating one above the other. So where does that leave us? Behavioral genetics doesn't hand us easy answers, but it reframes the conversation. It forces society to reconsider responsibility, potential, and intervention. Knowing that genes play a role doesn't excuse poor behavior, nor does it imprison anyone in a pre-written script. Instead, it offers a roadmap for understanding tendencies and vulnerabilities, nudging us toward empathy and smarter social policies. It's controversial because it touches identity, choice, and morality, but it's compelling because it's real. At the intersection of biology and life experience, behavioral genetics challenges us to rethink what it truly means to be human, and maybe accept that our behaviors are neither fully ours nor fully our parents'. Race and IQ hypothesis. People have long tried to make sense of why intelligence seems to vary across populations. The race and IQ hypothesis dives straight into one of the most controversial corners of psychology and genetics: the idea that some racial groups score differently on IQ tests because of inherited factors. It's a topic that sparks heated debate, mostly because it treads the thin line between science and social prejudice. At its core, the hypothesis suggests that genetic differences between races could influence cognitive abilities. Proponents argue that IQ, being a measure of problem-solving skills, memory, and logical reasoning, has a heritable component. Therefore, they claim, observed differences in test scores among racial groups might partially reflect underlying genetic differences. They often point to consistent patterns in large-scale IQ studies that show, on average, some groups outperform others on standardized intelligence tests. Supporters of this idea cite studies like the bell curve research, which collated decades of data showing a gap in average IQ scores between black and white populations in the United States. They argue that even when controlling for socioeconomic factors, some differences remain, suggesting a biological influence. Some researchers also highlight heritability estimates within groups, claiming that intelligence can be passed down, and by extension, might contribute to intergroup differences. But the evidence here is far from straightforward. Critics immediately push back, emphasizing how deeply environmental factors shape cognitive development. Poverty, access to education, nutrition, stress, and cultural biases in test design all have massive effects on IQ scores. They argue that what appears to be a racial difference is actually a reflection of inequality, not biology. For instance, IQ tests are created within specific cultural contexts, meaning they may favor the experiences and knowledge of certain groups over others. Historical oppression, systemic discrimination, and differences in opportunities cannot be overlooked as major contributors to disparities in performance. Alternatives to the genetic explanation are compelling. Studies focusing on enriched environments show that children from disadvantaged backgrounds can dramatically improve IQ scores when given access to better education, healthcare, and social support. This suggests that intelligence is far more malleable than the race and IQ hypothesis often allows. Critics also point out the danger of conflating correlation with causation. Just because a racial group averages lower on a test does not mean that genes are to blame. Social and historical context is crucial to understand these patterns. At the end of the day, the race and IQ hypothesis remains a hotbed for debate because it mixes complex science with sensitive social issues. While genetics play a role in individual intelligence, using race as a shortcut to explain differences oversimplifies reality and risks reinforcing harmful stereotypes. Intelligence emerges from a web of biology, environment, culture, and opportunity. So, even as researchers probe the puzzle of IQ disparities, the broader perspective reminds us that human potential can't be neatly boxed into racial categories. Rather than seeking deterministic explanations, the focus could shift toward understanding how society can nurture cognitive development for everyone, regardless of background. Blank slate theory. Imagine if humans started life as a completely empty canvas, a clean slate, waiting for life's experiences to paint who we become. That's the bold claim behind the blank slate theory, or tabula rasa as philosophers love to whisper in fancy Latin. The idea is seductive. Environment molds everything about us, from our quirks to our deepest beliefs. Nature takes a back seat. Nurture drives the show. It promises a world where change isn't just possible, it's inevitable. The core idea is simple but radical. Our minds, at birth, carry no preloaded software. Every fear, preference, skill, or habit is scribbled in by culture, upbringing, and personal experience. You are not born brave, fearful, artistic, or logical, you learn all that. John Locke first championed this centuries ago, suggesting that life is a blank notebook, and society's experiences are the ink. Modern advocates argue this framework is empowering. If everything about us comes from environment, then social engineering, education, and upbringing can shape anything. Bad behaviors? Correctable. Genius? Potentially teachable. Morality? Entirely learned. The slate is spotless, waiting for life's lessons. Evidence for this theory comes from dramatic examples of influence. Consider feral children raised without societal guidance. They struggle to learn language and social norms, showing the profound weight of environment. Studies in identical twins separated at birth reveal both sides of the coin. While genetics plays a role, the environment clearly sculpts personality, values, and habits. Cultural differences in morality, behavior, and emotional expression further hint that who we become is heavily steered by upbringing and surroundings. The blank slate theory turns the microscope on society, arguing that what we consider human nature is more often human nurture. But here's where things get messy. Critics argue that the blank slate is too neat a story. Evolutionary psychologists, like Steven Pinker, push back hard. Humans come preloaded with instincts, cognitive biases, and emotional wiring. Fear of snakes, attraction to certain social hierarchies, even the basic capacity for language. These aren't scribbled on from scratch. And if that's true, the blank slate underestimates the stubborn, built-in features that resist even the most intense cultural editing. The extremes of nurture-only thinking risk oversimplifying human complexity, ignoring the messy tango of genes and environment. Yet, the debate isn't all black and white. Even if humans aren't entirely blank, the theory forces us to wrestle with how much our experiences shape us. It's controversial precisely because it challenges the comforting notion that biology is destiny. It flirts with utopia. Imagine raising humans in perfect environments. And it warns against determinism rooted in DNA. Maybe we aren't blank slates, but the slate is far from fully written. Every culture, every home, every choice leaves a mark, subtly rewriting who we are in ways that genes alone can't predict. In the end, blank slate theory reminds us that while biology sketches the outline, life paints the portrait, often with bold and unpredictable strokes. Memetics. Imagine ideas as viruses. Not the sick kind, but the mental kind, units of culture that hop from brain to brain. That's the basic spark behind memetics, a field that treats memes as more than just funny internet pictures. They're replicators, evolving in the wild ecology of human minds. Richard Dawkins tossed this concept into the spotlight in the 1970s, suggesting that cultural evolution might mirror biological evolution. Some ideas survive because they're sticky, others fade away, much like species in nature. So what makes a meme thrive? Think of it as survival of the fittest for thoughts. Memes latch onto attention, spread through imitation, and mutate over time. Jokes, fashion trends, conspiracy theories, even rituals, these are all examples of cultural DNA in action. The key is replication. The more a meme can be remembered, shared, or acted upon, the stronger its evolutionary chance. Some memes exploit emotion, like fear or joy, while others manipulate social structures, giving a person status or connection if they adopt it. Essentially, memes aren't passive. They're clever little survivors riding the currents of human interaction. Supporters of memetics point to astonishing examples. Catchphrases that dominate decades, viral challenges that sweep the globe overnight, and enduring urban legends. These aren't random. They're evidence of ideas competing for cognitive space. Even religious beliefs and political ideologies can be seen as memes with astonishing persistence, shaping societies over centuries. Studies in marketing and social psychology hint at patterns too, showing how certain messaging hooks attention, is imitated, and evolves subtly to fit new audiences, echoing Darwinian logic. But it isn't all tidy. Critics argue that memetics oversimplifies culture, reducing complex social phenomena to a kind of mental Darwinism. People aren't blank slates. Context, power dynamics, and intentionality matter. Ideas don't always spread just because they're fit. Sometimes popularity is random or enforced. Some theorists suggest hybrid models, blending memetics with sociology, network theory, and cognitive science to account for nuance. Others dismiss it as metaphor rather than rigorous science, claiming it risks stripping culture of its human richness, boiling everything down to viral mechanics. Still, the lens of memetics opens fascinating doors. Whether you love it or roll your eyes, it challenges us to see culture as alive, competitive, and surprisingly predictable. It invites us to ask, why do some ideas explode while others fizzle? How much of our daily behavior is subtly shaped by invisible mimetic forces? And in a digital world where every click can amplify a meme globally in seconds, this framework isn't just theoretical, it's essential for understanding the modern mind and society. Memetics may not explain everything, but it's a tool for spotting patterns in the chaos of culture, giving us a peek behind the curtain of why we think, share, and believe what we do. The Biocentrism Theory. Imagine a world where humans aren't at the center of everything. A place where all life forms, from the tiniest microbe to the largest whale, have inherent value. That's the essence of biocentrism, a radical departure from the human-centered worldview that has dominated for centuries. According to biocentrism, life as a whole, not just human life, is what deserves moral consideration. It asks us to step back, question our entitlement, and reconsider our place in the grand scheme of existence. The theory is built on a simple but powerful idea: all living things have value in and of themselves, regardless of their usefulness to humans. This extends beyond animals and plants to even microscopic organisms, emphasizing the interconnectedness of all life. Biocentrism is not just about preserving species for our own benefit, but about recognizing that every organism has an intrinsic right to exist. In this view, humans don't stand apart from nature. We're a part of it, just like any other life form. Biocentrism calls for a shift in ethics, advocating for a more egalitarian treatment of nature where humans are not the ruling species, but fellow inhabitants of Earth. The core argument of biocentrism is simple yet profound. Life itself has value. The theory challenges the anthropocentric mindset that often sees animals and plants as resources to be exploited. By embracing biocentrism, we shift our ethical perspective. It's not about saving endangered species for our convenience or profit, but about ensuring that every organism can flourish on its own terms. Biocentrism demands that we consider the rights of animals to live free from harm and exploitation, that we respect ecosystems not for their potential human use, but for their own intrinsic beauty and balance. It's a call to acknowledge the importance of biodiversity, not just in economic terms, but in terms of life's interconnectedness and ethical dignity. One of the strongest pieces of evidence supporting biocentrism comes from environmental science. The destruction of ecosystems due to human activity is not just a loss for humans. It's a catastrophe for countless species, many of which we still don't fully understand. The collapse of one part of an ecosystem has ripple effects, destabilizing entire systems that other organisms depend on. We've seen this in deforestation, pollution, and climate change. The rapid extinction rates we're witnessing aren't just a statistic. They represent lives being extinguished, lives that have an inherent right to exist, just as we do. There are also philosophical and ethical arguments that give weight to biocentrism. One could argue that if humans deserve moral consideration for their ability to feel pain, then animals, too, deserve similar rights. The fact that many animals are sentient beings capable of experiencing suffering only strengthens the case for extending moral consideration to them. Furthermore, the idea that nature exists for human use alone is increasingly being questioned by those who advocate for a more harmonious relationship between humans and the environment. With climate change and the growing environmental crisis, it's become harder to deny that our traditional, human-centric views are not only unsustainable but unethical. However, biocentrism is not without its critics. Some argue that it's an unrealistic philosophy, one that doesn't account for the complex nature of human society. It's easy to say that all life has intrinsic value, but what about when it clashes with human needs or survival? Critics point out that biocentrism doesn't offer clear guidance in cases of conflict, such as when saving a species could mean the destruction of another, or when human development leads to the displacement of wildlife. Can we really say that an endangered species has more value than human life, especially when the human life is at risk? Moreover, biocentrism doesn't always provide a framework for how to weigh different types of life against each other. What happens when the interests of one organism, like a plant, come into direct conflict with the survival of an entire human community? Another critique of biocentrism is that it may lead to a kind of ethical paralysis. If we were to give equal moral consideration to all life forms, it might be difficult to make decisions on issues like urban development, agriculture, or even medical research. The theory could lead to debates about whether to prioritize human welfare over the rights of animals, creating a moral quagmire where every action becomes fraught with ethical dilemmas. Despite these critiques, biocentrism remains a compelling call for a shift in how we view and treat the natural world. It's a reminder that humans are not the only beings that matter, and that our moral obligations extend beyond our species. While it may not provide all the answers, it challenges us to think more deeply about our role in the world and to consider the rights and dignity of all living creatures. In the end, biocentrism isn't just a theory. It's a perspective, one that asks us to open our eyes to the incredible complexity and beauty of life beyond ourselves.